Hi, this is Travis Humble doing microphone check.
All right, if I can have your attention, please. My name is Morris. You'll be hearing from me throughout the day. Nice to meet y'all. I'm a PhD student working for Professor Bodhiseva and Professor Shalive and Professor Kildashev. I'll be MC today. We'll be hearing from Travis soon. But first, without further ado, Professor Sasha Bodhiseva.
Thank you, Morris. Hello, everyone. Yeah, that's a support. That's my support group. I love that. Welcome, everyone, to this in-person summer school. We do have a very exciting program scheduled. I am Alexandra Boltaseva, as you will see on my tag, but I go by Sasha, and I'm always in doubt whatever to put on my tag. So feel free, whatever you prefer. I'm a professor at Purdue University, but I also represent Quantum Science Center, where I lead efforts on workforce development. And hopefully this would be our signature event of the year, where we make a contribution to building quantum workforce in this country. First, I would like to pass the microphone, or actually that would be a virtual address, to our Director of Quantum Science Center, Travis Humble. And who?
Wonderful. Thank you, Sasha. Can you hear me okay?
Just a second. We will put you on a big screen, Travis.
Sounds good. Okay, so I think I may be ready to go. First off, let me welcome everybody to the Quantum Summer School. It's a pleasure to have you here. My name is Travis Humble. I'm director for the Quantum Science Center. I'm sorry I'm not able to join you today, but it is an exciting event for all of us. This is our second Quantum Summer School. Of course, it's the first time that we've been able to bring everybody together. I want to extend an extreme thanks to Purdue University for hosting the on-site component, and also to you for traveling and coming together this week to explore the topics of quantum information science and technology. I think this may be some of the first times that we've all been able to get together for an in-person event, and I know that everyone's excited, including our friends and partner at Purdue University, as well as the Emerging Frontier Center at the crossroads of quantum and AI. As Professor Boltaseva was saying, the Quantum Summer School is part of our commitment to building the next generation of scientists and engineers that the country needs to advance quantum science and technology. It's an important part of establishing a broad and diverse workforce. My personal belief is that we need the best and the brightest from every
But the
discipline.
audio channel is not joined, Morris. The audio channel.
Oh, Sasha, is there an issue?
No.
Sasha, can you hear?
Fortunately. Travis, can you hear us?
I can hear you, Sasha.
Okay. Unfortunately, we had some technical difficulties on this on our end. So I guess we just have to restart it, right?
Oh, no problem. Let me start from the beginning.
There is some feedback going on and we don't understand where it's coming from. Travis, do you have something, maybe live stream from the school open also?
A microphone?
If you have live stream concurrently open on YouTube, close it.
I'm having a hard time hearing you. I heard something about live stream.
Yeah, if you are having your YouTube link open, close that.
I don't.
Mic is right here. The mic is right here. We still don't understand what's going on.
Sure.
Are you sure it's not the live stream which comes with a delay? That's probably my voice, which you hear after delay.
So
That's live stream. So it's coming from live stream.
Mm-hmm.
It's the live stream, probably not on Travis's end. The live stream is somewhere here. Travis?
What about now?
Okay, let's try again.
Sure thing. You can hear me okay right now?
I'm sorry you have to hear me twice.
Well, it's a really important message. So I certainly don't mind starting at the beginning and welcoming everybody to the Second Quantum Summer School. It is, of course, a pleasure to have everybody come together. I know this is probably the first event that many people have attended in person. And so, of course, we're all very excited, including our friends and partners at Purdue University. And I'd like to extend a thanks to them, especially the local organizing committee, for putting together the event. The summer school is part of our commitment at Quantum Science Center to help build out the next generation of quantum scientists and engineers. This is an important part of our mission for the Department of Energy as well as the country. The summer school is intended to establish a broad and diverse scientific workforce. My personal belief is that we need the best and brightest from every discipline that is coming together to build out quantum science and technology. That's how we're able to establish a robust ecosystem within the United States. Now, to this week, you'll hear from some of those leading experts in the fields of quantum materials, devices, computing, and sensing, and there'll be lots of opportunities to get together and share ideas. Hopefully, you've put together a poster that you can present during the poster sessions, and then, of course, attend as many of the networking events as possible, because these events this week, the summer school itself, is a venue where you can form some connections that will last your entire lifetime for your professional career. Now, I would like to extend a special thanks to our sponsors for this year's event. That includes IBM Quanta and Cold Quanta. They are both vested in the QSC, serving as our partners and also serving as an important part of our workforce development and industry engagement efforts. So extreme thanks to all of you. And then to our members of our Industry Advisory Council, JP Morgan Chase, which has vested a lot in the area of quantum computing. And I, again, extend thanks to them for support for the summer school. Finally, let me thank all of the local organizers who have been part of the effort to put this together and pull off the second annual summer school and the first one held in person. In particular, I'd like to thank Professor Sasha Voltaseva, who leads our workforce development within QSC, David Stewart, who's the managing director for the Purdue Quantum Science and Engineering Institute, and Blake Wilson, who heads our postdoctoral and graduate student association. There's many other people behind the scenes working to pull this off, and I'm very grateful to all of them for making this a success. And finally, let me thank the students who have traveled and are joining online for participating in the second annual summer school, and we look forward to all the great things ahead. Sasha, I'll turn it back over to you.
Much, Travis. Thanks again. And as I already said, it's great to have you all here in person. And you know, when it's in-person meeting, even technology hiccups is like a human touch, right? If you are sitting somewhere, even in the comfort of your home, it's not the same. It's been 2 years when we planned an in-person event. And with all the success of last year's summer school, it's still much better, and it gives different feeling to have people on campus. Recently, my younger daughter asked me, when she comes from school, quite often we're just sitting on the Zoom meeting, and she said, "Mom, are you ever going back to work and start working?" And that's the time where we have to go back and start working. And I'm happy that today I can bring both my kids and all my academic kids and the colleagues and students and postdocs, both internally from Purdue Quantum Science and Engineering Institute, Purdue ECE, Purdue at Large, Quantum Science Center, and also our partner centers funded by Department of Energy. We have a very exciting program, as I already mentioned, and you all have a program in front of you, so you can read the big names that you probably heard of, reading the press releases and tweeters and being on the social media, because quantum is everywhere, and the speakers and the companies and institutions they represent are also all over media. I guess before we go to our exciting program today, I would like to thank one more time the local organizing team, and not only thank, but I would like them to maybe stand so everyone can see. Well, Morris is already standing, Blake and David. And whatever questions you have or suggestions or feedback or anything, please address it to us. And we also have the rest of our wonderful team there at the registration desk. With that, I'm very excited to hear everything which is planned for the upcoming days. And I pass it back to Morris. Thank you, everyone, for joining online, but mostly coming in person.
Thank you, Professor Botaseva. So we have our first speaker on deck, Professor Yang Chen. Professor Yang Chen is the Carl R. Horowitz Professor of Physics and Astronomy, a Professor of Electrical and Computer Engineering, and the Director of Quantum Science and Engineering Institute here at Purdue University. Professor Yang Chen's lab exploits quantum physics to manipulate electrons, atoms, spins, and photons in various materials and artificial systems, with the aim to uncover novel quantum phenomena and new states of matter, and to explore applications in quantum devices, nanotechnology, and energy. So without further ado.
Okay, thanks. Thank you, everybody. Okay, thanks everybody for coming out on Sunday afternoon. And also, Travis, if you're still online, thank you also. I'm sure the students all applied some quantum Fourier transform to the earlier part of your speech and got all the essence, a great welcome and the work you have done in the Quantum Science Center. And once again, I'm local. I'm director of Purdue Quantum Science Engineering Institute. And I want to extend a warm welcome to everyone coming to Purdue, if you're from outside, and to the summer school. It's wonderful we had this in-person event today. Again, we'll do this again, but again, one more big thank to the local organizers, David, Sasha, Morris, and also colleagues at Quantum Science Center. So I will give a presentation, but more from the material science point of view. So I'm an experimentalist. I work with the various quantum matters, but today I like to focus on the materials that emerging materials that may be important or may become important in future quantum technologies. So when I say emerging materials, that means they are not the main workforce today for today's quantum technology. Yet they have very interesting properties that may be important in future. In fact, I think one of the main missions of the Quantum Science Center is to identify and develop these emerging new material. Particularly, I will give some example. For example, new material for topological quantum computing, but others that may be important in future. So here's outline of today's presentation. And also the presentation is designed with the main target audience being a beginning graduate student that may be in the QSC or wondering about what's going on in QSC. So maybe it would be a bit boring for experts, but bear with me this Sunday afternoon. That's not be too tough, harsh. But I would give some general philosophical comment first on the quantum technology from the materials perspective. And then I shall talk about three, maybe just two. I tend to run a bit over time, but 2 to 3 materials that they're insulators. Particularly, they belong in the family of van der Waals 2D materials, which a lot of my group members actually work with this class of materials. First one being a 2D crystal, boron nitride. So that are really interesting and promising, I think, for quantum sensing, quantum emitters. These are single photon source for quantum communication, but even qubits. And then second part talk, I will talk about a class material that's hybrid between topological insulator and superconductor or topological superconductor that are emerging materials for so-called anion, particularly non-abelian anion or Majorana anion platform relevant for topological quantum computing, at least according to theorists, and that's a beautiful vision we'd like to realize. I probably won't have as much time, but I'll maybe very quickly mention third class of interest insulator, spin liquid material. That's also a very interesting platform that's explored in the center, okay? So these are all insulators. They are all interesting insulators. Some of them are kind of fake insulators. Topological insulator is actually a good conductor, but they have all unique properties for quantum information science as we go on. Okay. I don't know if it was designed to allow questions, but I personally certainly welcome questions during the talk. Okay, so again, this is Sunday afternoon. You might be sitting and wonder about life and civilization, but let's say remind us our civilization is actually in very much extent defined by the materials. We talk about Stone Age, Iron Age, and the classic computer is Silicon Age. And today we are entering already Quantum Age, but we don't actually know. We don't have a version of like silicon that defines classic computers. We're still very much open, searching for the important materials and many candidates. And if you look at the quantum technology today, right, the leading quantum technologies, perhaps the most already kind of in practice, so to speak, quantum communication, very much based on the ability to create and manipulate single photons and entangle the photons. For example, quantum dots in semiconductors. In fact, even their companies can sell these type of single photon sources. This one's based on 3.5 semiconductor and in the photonic waveguide, for example. Quantum sensing is coming along very rapidly based on various material. Maybe one of the material you heard most are these wonderful vacancies, defects in diamond that has wonderful level structures. It's also a spin qubit actually, but it has also optical transition to the excited state So it's optically active, addressable two-level system. There's a spin splitting, which is sensitive to things like magnetic field. Diamond is also a semiconductor, very large gap. We may call it insulator. From physics point of view, there's no real, I mean, the very large semiconductor become insulator. And then for the quantum computing, perhaps the most difficult technology, at least from a large scale practical point of view, but also perhaps attract the most attention. There are several platforms. We're here today, for example, in ions. But in the solid state, maybe the most well-known platform today is the Superconductor Josephson junction-based quantum computer used in, say, Google, IBM, so on and so forth. And the workforce there is a Josephson junction. That is junction between aluminum, which is a very conventional metal-based superconductor, two of them separated by aluminum oxide, which again is insulated. So all of these materials are based on relatively well understood, conventional and mature quote, but I use quoting about mature quote for classical technologies. They're still their properties, which are interesting, not well understood from quantum technical point of view, but they are relatively mature semiconductors or insulators or metal-based superconductors. However, as we look into the future, these are today, but as I'll describe, there are many other interesting materials, particularly in this presentation, a class of the van der Waals or layered, you may all probably familiar with graphene, but there are many other these layered van der Waals material that also possess very interesting properties, which are very promising for quantum technologies, okay? So I'll give you various examples, whether it's 2D crystal insulators like boron nitride or topological materials, or maybe magnetic, very interesting spin liquid insulators like lithium trichloride. One more philosophical, by the way, I should say, I won't go too much into this, but 2D material is a huge family of material today. So these kind of players all came around in the last about 10, 20, less than 20 years, about 10 years or so. There's really a huge family of these materials from conductors to insulators to superconductors, magnets, including spin liquids, topological insulators. And this, it just really mind-boggling. We have these hundreds, if not thousands of new materials we can work with these days. And being two different materials, it's like a sheet of paper or it's like a membrane you can transform on any other systems to make very interesting hybrid structures and integrate systems, which is impossible before. For example, just to prepare two-dimensional electron gas in conventional semiconductors is very challenging, require epitaxial growth, lattice match, but here those requirements are relaxed. And you can really bring a lot of interesting material together and build interesting structures, okay? Of course, you already heard the wonderful new tool of these tristronics. I won't go too much into, but these are a lot of interesting degree freedom introduced by two-dimensional materials, okay? The ability, it's very liberating in a way you can bring materials very different, electronic, magnetic, optical, thermal, etc., probably together to have emergent functionalities, okay? So another viewpoint, okay, I like to think about this. My group also work a lot on spintronics, and I like to think interesting quantum material from the view of spins. If you really think about, maybe in the past, certainly in the silicon CMOS, charge is the king of the information carrier. But I personally think of the spin degree freedom, we're going to see increasing utilization of this degree freedom. And in some sense, spin, ultimately spin is two-level. That's simply spin, just two-level, right? Up and down. It's the kind of the quantum system, simplest. And it also underlying almost all the interesting so-called quantum materials we studied today and we believe to be very promising for future quantum information science. In this organization, for example, magnets, it just spatially ordered spins. If you fix a location, you can predict where spin points. Okay, so that's a spin position order. And topological materials like topological insulator has a spin momentum order. If you fix the momentum, you can predict which direction the spin points at, right? So I like this duality between real space and K-space, which will come up later in the talk. If you look at superconductors, which is workhorse of today's solid-state quantum computing, it has this spin momentum entanglement. Namely, if you think about simply superconductor, which is a Cooper pair, the wave function is a BCS singular Cooper pair wave function. It's paired between electron with one spin in one momentum with the opposite spin in the opposite momentum. But then with another part, which is the opposite type of momentum for the same spin, so it makes a singlet pair, right? So in other words, if you fix momentum, you still actually don't know the spin. But if you take any measurement, you get the spin, then already you know the spin should be opposite in the opposite momentum. So there's the spin momentum entanglement, which is key to superconductivity. And then finally, the spin liquid materials, which I probably very briefly mention at the end, has a spin position entanglement. It is kind of a quantum disorder version of magnets. The spins are fluctuating and all the time. In the simple picture, if you give a position, you don't know the spin direction. But there's long-range fluctuating correlation. If you tend to see one spin points this way, you can actually gain information about where spin may be in a different location. There's a long-range, non-local entanglement. By the way, a version of the spin liquid, at least mathematically equivalent a version of spin liquid, has been realized in cold atom system, irritable atom. That's probably, I think we heard in last year's summer school from Misha Lukin's talk. So this is actually super interesting. So this is a demonstration that spin is at the core of a lot of interesting quantum materials. And even more so, when you interface different classes of these quantum materials together, you create a system that has a very interesting functionality that's important for quantum technology. For example, as I mentioned in the second part of my talk, the hybrid between topological materials like topological insulator with a spin momentum order with a superconductor with spin moment entanglement give rise, it's a platform that give rise non-abelian anions known as a Marana modes that could be important for topological quantum computing, at least one of the platform. Of course, the spin liquid material itself is also conjectured as another very interesting platform for that purpose. And let's not also forget, even in the insulator, like boron nitride, which I'll mention soon, it contains defects which act like a two-level system. In fact, the spin qubit, it's optical active, can be, it's also quantum emitter. That's already very interesting, especially when you can use this kind of spin qubit to perform quantum sensing of these other interesting material. I think that's an emerging, very interesting area and of research in this paradigm. Okay, so one more before I enter. If you take a historical inspiration, you realize in the classical computer, we actually start out not with the silicon, but with the metal vacuum tubes. And then first transistor is actually, by the way, is actually based on germanium. Purdue actually played a very important role developing those very high quality germanium in the old days. So the breakthrough really did not come from making metal vacuum tubes or even germanium transistors better. It actually comes from identifying much better materials that's almost 20 or 30 years after the first classical computer. So even though today, for example, some leading quantum computer, very impressive progress, of course, based on, for example, conventional superconductors and Josephson junctions, such aluminum oxide I mentioned. I think we should have a sense of kind of open-mindedness here that the future, maybe several, I think within our lifetime, certainly I actually see when we realize there's very large scale fault-tolerant quantum computing that can transform every aspect of our life, design new drugs, new materials, solving energy crisis, prevent disease, so on and so forth. And that material may not, based on today's leading candidate material. So I think we should be open-minded and look at materials that has interesting properties that may become tomorrow's workhorse of quantum technology. So let me start with giving some examples of this very interesting 2D insulator, boron nitride. I think has many promising properties in different aspects. But again, boron nitride in some sense is very similar to graphite, except instead of carbon atoms in this honeycomb lattice, you replace them with the boron and nitrogen atoms. So you break a so-called AB sublattice symmetry that opens a very big band gap, several EV, maybe 5 or so, in this material. So it's a very good insulator. Okay. But before I go further into boron nitride, let me remind you, let me start with something interesting example of quantum sensing. So I already mentioned this is currently one of the famous workhorse of quantum sensing is the vacancies in diamond, okay, which has interesting spin levels, which change with magnetic field. You can also address it optically. So that's a basis people have already used very successfully. For example, there's earlier work from Jacobi, a QSCPI, and also Prame. When he was postdoc, he's also in QSC here at Purdue, explore using NV-centered study magnets such as the EEG, so on and so forth. And here at Purdue, my colleague Vlad Shailev, working in collaboration again with the Prame and my group, and also Berkeley Center, this is a recent example using these NV-center to measure the magnetic fluctuation from a technology important conventional magnet, such as coffee iron boron, we call coffee B, controlled by a kind of piezoelectric substrate. This is in some sense a proof of principle. The way it works, where you change the, for example, apply magnetic field or even apply voltage, you can tune the magnon spectrum of the magnets to tune the off and on resonance with these NV center levels. And when you do that, here the fluctuation source, which actually changes the T1 time, right? Or the NV is controlled by this mag fluctuation. So you can increase this T1 time or make it shorter. This is actually making it shorter when the magnet magnetization is switched by this electric voltage or strain. In one sense here, you get a bad qubit because of very short T1 time, but you get a very good quantum sense because this shortening of T1 indicates a magnetic transition here. So this is a nice proof of principle. And we would very much like to apply this kind of scheme to many other interesting magnet materials. And a lot of those interesting materials turn out to be also van der Waals layered materials. So it's nice to have a 2D material or layered material version to can do many of these, okay? So, so here I take one of my favorite local example. I think it's a beautiful work creating, turning boron nitride. You can start with a clean boron nitride, but then creating defects. So this is work from our Purdue colleague, Professor Tongtang Lee's group, working in close collaboration, also with several QSC PIs here, and we certainly like to work even more closely with Tongtang in QSC in the years coming forward. And the way they create the defects to ion implantation, in this case, I believe helium, that you can implant these defects into these materials. In this case, they were able to create so-called boron vacancy VB minus defect, which also has a level structure with there's spin splitting, but it's optically addressable. There's excitation to excited states. You can address this optically. You can read out by so-called optically resolved magnetic resonance, right? The way you can drive this transition by microwave. This is on the order of a few gigahertz, but then the fluorescence signal actually depends on the level of situation here tuned by microwave. So this was successfully done. And more importantly, one challenge of these boron nitrides, they are not as optical bright, but already in this work, they use a nice technique, which you'll hear more, I believe, from Vlad's talk, probably later today. You can use plasmonics to enhance this kind of optical emission signal from quantum sensor qubits like this. So this is certainly already done by this very simple thing, just placing it on some kind of gold structure. This particular defects, if you look at emission, is emit about, has a PL about 800 nanometer. And clearly, one exciting thing is it's optical controlled PL signal, or this ODMR, clearly shows a splitting at when you turn on the magnetic field. So this is basis magnetic field sensing using these defects, okay? And I should say, this is very active research currently. There are many other groups doing similar things. For example, this again, the T1 time, which you can use technical relaxometry, depends on many environmental factors, including temperatures, phonons. This is a recent work from, I believe, Würzburg in collaboration with the Australian group, which actually pioneered this boron nitride defects. And a recent example from UCSD using boron nitride on the van der Waals magnets. In this case, a relatively simple metallic van der Waals magnets, iron germanium telluride, and can see the magnetic magnetization and phase transition sounds, etc. One more thing I think is very interesting. Very recently, I think Tongtang's group were able to demonstrate these, you can use these materials actually further sense the nuclear spins around these VB minors. And here the transition become megahertz, the nuclear levels. You can even start to do these optically pumped NMR measurements. I think it's a very interesting development to see this in a 2D material boron nitride, because if you think about, in a very general sense, NMR is actually perhaps the oldest quantum sensing, although it's most usually done on the ensembles, right? If you're a chemist, you use it all the time. If you need to go to the hospital, hopefully not, but you may already seen this. But this is all done on very bulky materials. So there's a dream. People would like to scale down these kind of NMR to very nanoscale samples. NV Center has already been explored in this context. I think things like 2D material NMR, boron nitride, that can do this in the layered, potentially, if one day you can imagine transfer one layer or a very thin membrane onto other materials or molecules on top of this material, you can do this kind of NMR measurements. That'll be very exciting. So I think this is an important direction. Another example, quantum technology to pursue with these 2D materials. Let me slightly change to a different example. Also, my colleague, Vlad Shalev, you'll hear from him later. Maybe I shouldn't go too much into His group and Sasha's group and others, we collaborate also, using, this is work by Xiaohui, a student in his group, using AFM tip basically to kind of punch or damage locally the boron nitride and create holes. And interestingly, with maybe roughly half time, the yield, I guess, could be better, still need to improve, but can create these arrays of quantum emitters, single photon source. Here's evidence. When you do this coincidence measurement, if you have a single photon source, they can never arrive at the same time. You try to split them and look at coincidence, right? So you have a dip at 0 time delay. So that's the if G2, the so-called G2 or hybrid boron twist measurement is less than half or approach 0, you have a good single photon source. I think this is a pretty good yield. About half time, you can get this defect, each of these whole to be a single photon emitter. I think pretty exciting. Note, they emit PL is about 600-ish nanometers. So it's very different from that 800 nanometer BB minus defect I showed earlier. In fact, Xiaohui has verified these are not those spin sensitive, quantum sensitive defects. So, okay, it's not good for both, but nonetheless, this is very interesting to have these arrays of quantum emitters. One of the dream, you heard actually last year's summer school, I think this is still a technical challenge. One of the dream is if we have ability to really have well-controlled these quantum emitters or spin defect or sense, even quantum sensor created in an ordered pattern, that would be tremendously exciting. For example, if you have ability to create them in the length scale, let's say 0.8 times the wavelength, you heard from Susan Yelling last year, probably she'll talk about this again this week, you can realize something known as a quantum mirror, which are very exciting. You could have, if this is a mirror, I like that cartoon Susan used to show, you can have maybe in the mirror, you can see a sleeping or maybe dead version of me in the mirror you can see. So you can have this very interesting macroscopic superposition if you have those ability. So that's one future direction, I think very exciting, which require ability to place these defects, quantum emitters at well-controlled positions with a good yield, okay? And another exciting direction, second dream, is to create these particular spin qubits or those magnetic field sensitive spin defects that I showed earlier. If you can create individual those defects also in an array, that's very exciting as well. Already ensemble people have used, as I showed in the example, to sense the quantum materials. But if you can create or controllably create them, you can probe quantities such as many point correlation function, which is a big thing theorists like to talk about when they characterize many body systems. The exciting measurement from atomic systems, ions and cold atoms, measure these kind of many body correlation, which is very, very difficult in quantum materials. Usually people are happy with doing 1 point, 2 point correlation function in transport or scattering. But if you can probe this higher order correlation function, maybe with an array of these sensors, that will be very important development in quantum materials, in my opinion. I think that's an exciting direction. And certainly we'd like to know how to do this, maybe translate ideas from the many body theory, but also AMO physics into this materials platform. I think that's also a very important direction of the work. And their preliminary work also ongoing locally with the various groups working together, placing these spin defects on magnetic materials of various kinds. So let me wrap up this part on boron nitride to say, so far I talked most about interesting defects, or defects beautiful, right, in the diamond boron nitride. But the clean boron nitride is also very nice, actually. Let's not forget about that. In fact, that's one of the first reasons boron nitride became so popular into the material, is that people placed graphene on boron nitride and were able to immediately boost the mobility, the kind of transport power of graphene to a very high level. And my former student, now he's a professor in Penn State, did this very simple experiment. Just look at one of F noise of a graphene as a conductor on boron nitride, and that's immediately an order of magnitude improvement compared to, say, on silicon oxide, which is a common substrate of graphene. And this is a very simple experiment, but it might be. So there turns out there's some interest in the ion trap community, try to explore, I think a lot more work to be done, better electrodes. So it turns out in the early days, some of the noise source in ion trap come from also these metal electrodes. Maybe when laser noise become better, that become an issue again, I don't know. But then improving these electrodes, for example, using graphene coating, there's one idea put forward. And I think there's boron nitride can play a role as well, together with the graphene, for example, enable those very low noise electrodes, surface electrodes. Here's another example, how boron nitride may help another very leading candidate qubit, which is Supercondition Junction. So again, this is a very simple exploratory experiment from a postdoc here, now Professor at Wyoming did. years ago, actually, only published very recently in collaboration with Robert McDermott in Wisconsin, who's expert in superconductor qubits, is to just build a Josephson junction using boron nitride as tunnel barrier. As I mentioned earlier, the traditional Josephson junction used aluminum oxide as tunnel barrier, which is amorphous insulator. And there are a lot of these mysterious two-level defects, things like that in these amorphous insulated aluminum oxide, which is known to be an important noise source in these Josephson junction qubits, or even just Josephson junction itself, influence the critical noise, for example. And by replacing aluminum oxide with the boron nitride, so he built I guess one of the first boron nitride-based Josephson junction, in this case between a niobium diselenide, which is also 2D material superconductor. Another superconductor is a metal niobium. So it's kind of hybrid version of 2D material Josephson junction. So you get nice Josephson junction behavior. But most excitingly, when you took this device to Robert's lab in Wisconsin, the noise, again, one of noise measured in the critical current is already at least several times lower than the comparable traditional junction made of aluminum oxide. This is actually upper bound because it turned out it's instrument limited. The real noise is believed to be even lower. So this showed these boron nitride, just replacing the conventional aluminum oxide tunnel barrier by boron nitride could already be quite promising to improve the superconductor Josephson junction and qubits. And of course, very beautifully, MIT Lincoln Lab took this to a very impressive level, incorporated boron nitride into the transmons and replaced their capacitors. So these capacitors, inductors, now if you use boron nitride, they can, these dielectric loss is one important issue in superconductor quantum circuits. And they showed boron nitride offer very competitive material and also give you much less physical footprint when you use 2D material like boron nitride. So this is, I believe, in future, we could see really interesting importance of these 2D materials such as boron nitride, even in superconductor quantum computing. So I think that's the first part. So maybe there are no burning questions. Let me move on to second part, where I'll describe so-called emerging anion materials. Particularly interesting is so-called non-abelian, the material that can realize so-called non-abelian anions, which many of you probably heard, is believed to be a workhorse for a very new form of quantum computing that is fundamentally more robust, more immune to error, called topological quantum computing. I should also advertise there will be a workshop organized by Quantum Science Center, I think in just a few weeks, dedicated to kind of manipulate anions. So check it out. So probably we all know this, our world described by electrons and fermions, we're based on this. And fermions, if you exchange two of them, you pick up a minus sign. That's the reason you cannot have both of them in the same quantum state. They will stack up to have these Fermi level. That's the actual basis of our entire periodic table and our life, and so on and so forth. Bosons, of course, very different. If you exchange them, you get +1, no minus sign, and they can all condense into the macroscopic condense into ground state. And that's the beautiful boson condensation. And basically, conceptually, broadly speaking, the basis of things like laser, superconductivity, superfluid. So that's also very important. Anion is something more strange, which actually rarely, but has not been utilized, so to speak, because it's fairly exotic quasi particles. In condensation, we know when we put atoms together or electrons or whatever in the particles in the many particle system, the system, you worry about their ground state, but then away from ground state, there may be excitations or quasi particles that may behave very different from individual constituent particles. So one of the first example of anions, I should say the concept of these anions actually was discussed even earlier in high energy physics quantum field theory, but in the real materials, the first example is actually this beautiful quantum Hall systems in condensed matter physics that emerged in the early 80s. And just briefly to remind you, the quantum Hall system is a two-dimensional electron systems. When you apply a magnetic field, it becomes, the electron have these Landau levels. If you, occupation between Landau levels, it's like insulator, right? Then within this system is insulating, but then the Landau levels will disperse up near the edge. You have these conductive modes at the edge, which have a fixed direction, there's chiral in the magnetic field. So that's integer quantum Hall effect discovered earlier. But just soon after, people found even in the even higher magnetic field, so this integer quantum Hall effect required the ratio of the electron numbers to the strength of magnetic field or the available magnetic flux quanta, so to speak, to be some kind of integer. So your Campbell potential is somewhere in between Landau levels. But even if they are a fraction, so your Campbell potential Fermi level is within the lowest Landau level, for example, the system can also achieve some kind of dramatic quantum Hall state, which is the famous fraction quantum Hall state. And that is a very iconic many-body quantum state, which cannot be understood from the simple part of physics. And people already realized that for example, near this 1/3, the quasi particles here are not electrons. They are particles carrying fractional charge, in this case, 1/3 of charge. That's already shown by experiments. And also they carry fractional statistics, meaning when you exchange them, you got neither +1 like bosons or -1 like fermions. You get e to the I theta. Theta is a number which is not 0, nor pi. Pi would be -1 for fermions. You get something like pi/3, for example, for near 1/3. And this is known as abelian anions. Let's be a little bit more clear. This has been also shown experimentally, one of the most clear evidence that actually came locally from the group of Mike Manfra, also QSCPI, using this interferometry device, showed these patterns of interference, which is direct observation of these kind of anion phase for these at least non-abelian anions. But fractional quantum system is extremely rich. In fact, the holy grail there is something even more exotic. Around some other fractions, the excitation is believed to be something even more strange, which is known as non-abelian anions. That's actually the holy grail people are pursuing these days in the condensed matter physics, which is the prime platform for topological quantum computing. Again, just to remind you, now in non-abelian anions, when you exchange these two particles, you don't even get a number phase. You get a matrix. So that quantum state, first of all, has to be represented by vector, right? And it's a matrix. In general, the two matrices will not commute with each other, okay? So it's a vector. The ground state has some kind of degeneracy. When you do this exchange, you have to have these matrices involved, and in general, they are non-abelian. And for that reason, when you braid them, exchange them, the system kind of remember the history. And more so, it's immune to the local small perturbance, okay? So had this braiding pattern, which is topological kind of knot, right? A knot is fairly robust. If you wiggle around the knot, if you don't break the wire, you won't remove that knot unless do something dramatic. So local motion is not going to be as a big problem. So using this topological grid frame to encode information, of course, is the holy grail that people pursue in topological quantum computing. So that all sounds beautiful. In fact, it's very beautiful. It's one of the most beautiful chapters in mathematics. The challenge is whether we can find real materials that realize this beautiful physics and actually be utilized. So that is a direction that's driving a big part of research in a number of different platforms. So these are some of the major material platforms people have been pursuing, these non-abelian anions. These are not even all the platform, but these are a few important ones, or perhaps most promising one from the building a realist devices, at least in my opinion. The first one is what I already mentioned, the fraction quantum Hall effect in the 2D electron gas. I think gallium arsenide is still probably the highest quality to workhorse, but the graphene, also studying this center, like in Andrew Young's group, the Santa Barbara, is also emerging as a very high quality 2D electron gas. This data, local data on gallium arsenide, but graphene has become very competitive. They have these fractional states, and not just 5/2, various fraction quantum Hall state that are proposed as candidate to realize these non-abelian anions. We need experimental proof, of course, but that's one of very important platform. And these tend to require very high quality materials. Some of these are produced locally here. Generally speaking, very low temperatures, millikelvin dilution fridge, and high megafield being quantum Hall systems. Then there are other two other major classes of material platforms. They are all broadly speaking to be some kind of Majorana fermion, or in fact, we have in this field, the terminology is a little bit loose. I will try to explain it better later. But let's broadly say Majorana fermion, even though we are really after non-abelian anions, which are not Majorana fermion. But there's a bunch of platforms known as the Majorana fermion platform. Actually, even on the theoretical level, things like fractional quantum Hall like 5/2 is also very closely related, at least intellectually, to these platforms. It's based on a topological superconductor, different kind of that S-wave superconductor I mentioned earlier, right? With S-wave single pairing, but it's a P-wave superconductor with the property that the defects in that P-wave superconductor, whether it's the end of a wire or a vortex, can trap a bound state we call Majorana zero modes. So what's really anion is actually not Majorana fermion. Majorana zero modes, although it's related. They behave as a non-abelian anion, have this anionic non-abelian statistics. Okay. And the there's various important material platform in this case for topological superconductor. So I can broadly divide them into proximity-induced topological superconductor, which probably most actively pursued right now. For example, the famous Microsoft project, which is trying to realize this by coupling superconductor with a one-dimensional nanowire made of a strongly spin orbit coupled. So spin orbit coupled system has this spin momentum order I mentioned earlier. When you try to combine that with superconductivity with a spin momentum entangling, some interesting happen. Near the ends of the wire, you're supposed to nucleate these Marana zero modes or anions. We actually heard for those in QSC, we just heard a very beautiful talk last Thursday by Chetan actually explaining the beautiful physics instead. So I will not go too much into these semiconductor-based platform. And then they are very similar, conceptually at least, approach either coupling superconductivity with the edge, so-called spin helical edge mode of a quantum spin Hall state, which is also known as two-dimensional topological insulator, or coupling to the surface of a three-dimensional topological insulator, which I'll explain a bit more. And at the interface, all of these approach is trying to create a proximity-induced superconducting state at the interface between superconductor and these various materials that behave like a P-wave or at least has a component which is a P-wave superconductor. And then theorists told us, like Kitaev told us that then near the vortex or defect of these P-wave superconductor, you can have these Marana zero modes. And there are also materials, which I won't discuss too much in this talk, which by itself, without using these heterostructure, itself is already both a so-called topological materials and a superconductor. These high TC iron-based superconductor is one example. There are other examples. By the way, some of these materials also studied actually in QSC. And then again, if you have superconductor, you can have vortices, and bound to the vortex, also you have these Marana zero modes. So this is actually a pretty large class of materials, broadly all known as topological superconductor, either created by proximity coupling or created just through materials discovery or engineering that supposedly would generate these Marana zero modes. And then a third class of materials are these spin liquid materials or quantum spin liquid and ruthenium trichloride, which probably I only have a few seconds to mention, and is one example where naively it looks very different. So all these others are charge-based systems. So here, there's a reasonably well-defined approach how to build devices to manipulate, control these, detect these anions, and maybe even braid them. It's more difficult for these charge-based, for these spin-based, and they are insulators. You cannot directly do charge transport devices. But they have recently emerged to be very interesting. People actually start to have various ideas, and mathematically, at least, the excitation in these materials can be mapped to be the same kind of or similar kind of non-binary anions, so the emergent quasi particle, even though they do not carry charge, but they are also support non-binary anions and also Marana fermions in this system, and people very much be able to directly manipulate them and build device on these materials. So this is a frontier, maybe more challenging, but recently there's a lot of ideas popping up to become a really exciting frontier, very much pursued in this center as well. Okay, so I will mostly perhaps focus on these this platform, which is the interface between topological insulator and a SQA superconductor. At this interface, which is two-dimensional surface, it is believed you would realize a 2D P-wave superconductor state and supporting these Marana zero modes. And I will primarily give some examples how to improve the materials, start building devices. These, the experiment techniques allow us to pursue, which I think is still a very challenging route, but the important components to experimentally pursue this. So I mentioned there are other platforms I won't go into, and just mention in the passing Marana fermion. So this is a little bit clarification of terminology. This terminology, Marana fermion, originally were talk about in high energy physics. Right? People, of course, part of quantum science center is high energy physics. For example, detect dark matter, and neutrino was thought to be a Marana fermion, which means basically just means a fermion which is own antiparticle. Right? But then there are other more exotic Marana fermion candidate. If you have a supersymmetry partner which says every boson has a fermion partner, then photon has a partner, which called photino, which would be a Marana fermion because photon is its own antiparticle. Some of these were even proposed as maybe the kind of a dark matter, which is a big part. Detection of dark matter is a big part of the quantum science as well. Maybe not these particles, so there's long history. In the condensed matter system, as I said, something interesting happens when you bring superconductivity, right? We have these spin momentum entangled singlet pairing into a electron system. So this is ideas put forward by various theorists. They told us that when you do that, something interesting happens. In the spin helical electron system, by spin helical, I mean spin is locked to the momentum that I gave you emphasized earlier. But for example, here, the surface state of topological insulator, which one example of spin helical system. If you fix the momentum, the spin direction is fixed. So the Fermi surface, at each momentum, there's only one spin state. So that's very different from the, from requirement of the superconductivity S-wave pairing, where you require both spin states at each momentum. So you cannot actually come up with this S-wave pairing conventionally in the spin helical electrons. So in order to force them pair, you have to add the triplet channel. Okay, so then you can cancel this other half of the channel and to come up something like pair. So this, again, this is simplified a bit hand-waving argument, but you can appreciate you create a channel which this triplet channel is a P-wave superconductivity. And then theorists told us first of all, why we still call them Marana fermions. So if you just do this, right, there can be moving itinerant particles in these topological superconductor, which are still fermions. But then the superconductor has a wonderful property, won't go too much into, but it kind of, because condensate is a condensate of Cooper pairs, you can sort of turn a particle into antiparticle electron hole by exchange with a huge condensate with electron pairs. So superconductor can kind of exchange between particle and antiparticle. So that allows to already create Marana fermions with the fermion statistics. But what is really interesting, people are looking after, is when you have a defect, when you bond these Marana fermions into a defect, could be vortex, then you don't have any fermionic dispersion, like this anymore. You create these states pinned at the zero energy, known as Marana zero mode. It is these Marana zero modes which were shown, at least theoretically, to obey non-abelian statistics, not the itinerant Marana fermions, but they are very much related. But so people looking for these Marana zero modes bound to the defects, could be end wire, could be vortex that carry these anionic, non-abelian anionic statistic, which I believe to be the workhorse of topological superconductor, quantum computing. So what is topological insulator? I've been spending time talking about topological insulators. And very briefly, it's this, first of all, it's not even insulator. It's actually a good conductor. It would be insulator if not for topology or strong spin orbit coupling that inverted the bulk band gap of semiconductor into, you invert the usual order of valence and conduction band. Okay, questions? Right? But it has a different topological so-called number in the band gap. But outside this insulator, you have a conventional vacuum or trivial insulator. So they have the cross generate some kind of gapless modes at the surface or boundary. And these gapless modes turns out to these Dirac, graphene-like 2D electrons, which actually have this additional important property. The spin is locked to momentum. Okay, if you fix the momentum, spin is always in plane, at least near the Dirac point, perpendicular to the along the surface, is perpendicular to the surface normal, and the Fermi surface have these spin tangentially wrapping around the momentum. So these are the spin helical, this is called helical spin momentum locking. Also, Kitaev calls it spinless because there's no spin degree freedom. That's the basis. Then you bring superconductivity, theorists told us, you create these Marana fermions, and then you bond them into with defect Marana zero modes. Okay, so this is a basic picture, and then experimentally took a while to demonstrate all these properties. Some examples of key topological transfer properties are once you have these. So to very briefly speaking, topological insulator is like half the Dirac graphene. Graphene, each Dirac cone has actually even a quarter for each surface, but it has only one spin state. So you realize so-called half integer quantum Hall effect and half integer Ahern-Born effect. I won't go into, but these are some of the screening you have to do to show you have very good 3D topological insulator. And then where the electrons only occur on the surface, by the way, the wave function of those electrons about a nanometer or so, pretty narrow. And these spin helical electrons on the surface is a platform, is a basis. Step number one, that's where you want to get, okay. It is also the basis, actually, I should mention, to getting the spin helical electrons is also the basis for the semiconductor nanowire approach that pursued most famously at Microsoft, which is based on you have a nanowire of strong spin orbit coupled semiconductor, for example, indium marsenite or indium antimony, which is described by this so-called Rashba Hamiltonian. So it's basically spin orbit coupling splits the usual parabolic dispersion into two spin split copies. And if you apply magnetic field, that's transferred to the spin orbit coupling field. You open a gap here. And then in this gap, you can mimic situation of a topological surface state. So when the Fermi level is in this gap, at each moment, you only have one spin state. Then you can apply Kitaev argument and other theoretic argument to say, if you bring superconductivity, the same thing would happen. Now you have only one spin state for each momentum. You're forcing into the S-wave pairing is impossible. You have to introduce a P-wave pairing channel. Then you create this effect. So this is actually the similar intellectual basis underlying both topological insulator and these nanowires. In reality, it's difficult. It's actually one of the nice thing about each platform, just like quantum computing platform. These are topological quantum computing platform. Each platform has own advantages, disadvantages. The semiconductor perhaps most studied because it's most compatible with industrial fabrication. But it's actually challenging to illustrate this kind of control these single particle band structure. Even though material is supposed to be quite clean, the real material is more complicated. There's still a lot of issues uncontrolled, are not understood very well. So it's actually, this simple picture is very much oversimplification. It's, in fact, even to demonstrate the underlying what nanowire really have this nice spin helical structure, you're really working here. The simple picture is difficult to realize experimentally. Now, topological insulator also has its own challenges. It's much less mature even compared to this material, but it also has its interesting advantages and features. One of them is this single particle spin helical band structure is already very well established. This is RPAS photon emission data shows over a very large range energy. If, that's not easy, but if you can put your Fermi level in this large gap, you can actually directly already have this spin helical electrons to work with. So, and then theorists already told us if you can do that, right? It's all pretty simple. It's your job to come up with good material, good enough to do all of this. But then there's a well-defined theoretical protocols. By the way, in the case of topological insulators, the Foucault proposal and other schemes, by fabricating islands of superconductors, you can start manipulating. These are basically Josephson junctions, a network of Josephson junctions between superconductors and topological insulated surface states. You can manipulate, you can nuclear Majorana zero modes at various places in this Josephson junction network and move them around, even braid them. So there is a reasonably well-defined pathway, at least theoretically, how to do this, build devices. And we can also benefit a lot from the schemes developed and pursued in the case of the one-dimensional nanowire, even though it's somewhat different physical system, but a lot of ideas can still translate with some adaptation, can make system, for example, 4 Majorana zero modes, make one topological qubit, how to kind of manipulate them, fuse them, can demonstrate qubit operation. So there's a clear, reasonably clear pathway how to do this in a charge-based anion system like this. The challenge is actually come up with a good material, actually can allow you to do all of these. So let's see, what are challenges? So I already went through most of these. And even though in the earlier generation experiment, for example, this is beautiful STM experiments from Shanghai, I think, that is STM experiments, not transport device measurement, but it's a tunnel into the vortex air formed between a superconductor at interface between superconductor and topological insulator. And people see a zero modes, a resonance at zero energy, which is consistent. Perhaps this is a Majorana zero mode. As many of us heard, having a zero mode is not necessarily a Majorana zero mode. There are still a lot of unknown questions. So this is maybe the necessary but not sufficient condition. And we know many of these part of a material challenge, both in the induced topological superconductor and even intrinsic topological superconductor. So similar measurement has been done on these intrinsic topological superconductor. There are many, many material challenges. For example, first of all, you need superconductivity, right? You need to bring two things together. You need superconductivity with good superconductivity behavior, which may suggest you need a large superconductor gap, maybe high temperature, high carrier density, a good, but you also want to minimize carrier density near the Fermi surface, which we'll get to in a minute, which primarily you want to minimize these conventional carriers, either in the bulk or influence from these constant materials that mess up the only one thing you care, at least to the 0th order, you want to get that Maran zero modes, but there's only other particles, right? Non-topological anions that kind of interfere with your operation. So here's one. So people work very hard to clean up topological materials, topological insulators, so to speak. So even the first challenge I mentioned, you have to minimize the bulk carriers, which is one of the common things in topological insulator that mess up this nice scheme, for example. So in real topological materials, it is not turned out only the spin-hit electron that's conducting. You have a lot of other conducting electrons, most commonly coming from just bulk materials. And people worked very hard over the years, including my group, and to clean up topological insulator. So it turns out the most famous topological insulator, for example, bismuth selenide, is not necessarily a good one because the Fermi level is usually very high in the conduction band. And mostly you're dealing with these conduction band bulk electrons. Very little chance to access topological spin-hit surface states, at least in the common bismuth selenide. You have to work harder to make materials. All of these are layered materials like this. They have to add more elements like antimony and tellurium to the bismuth and selenium. And one of the best bulk topological insulator developed here at Purdue was this 4-element one, which is still one of the best in the bulk topological insulator. It has the very low bulk carrier density. In fact, it cannot be measured at low temperature. The Fermi surface shrink to almost like a point, which is a very good sign. So there's no bulk carrier at low temperature. You're really in a bulk gap. And at low temperature, instead of showing a metallic behavior like bismuth selenide coming from bulk carriers, you have truly bulk insulin behavior that's saturating to a surface conduction. Only in these materials, and very few examples of these kind of materials, you see these topological transport like half-integer quantum Hall effect, so on and so forth. And here's one, I highlighted one example of material challenge of issues. So people have done, this is example actually, scanning tunneling data into vortex of a candidate topological superconductor, which is one of those iron high-tensor superconductor, but physics is very similar. So in this vortex, you commonly see these zero mode or zero bias peak. But if you look very closely, there are other peaks also very close to zero energy, which can be very easily confused with the zero mode if you don't measure carefully. And one of the most famous these so-called spalling states are the famous Canoli-de Jonge CDGN states in the system. And they occur typically on the order of the gap of superconductivity squared divided from the energy. So the goal, at least for this, to avoid this to mess up your topological Marana state, you want to have a good superconductor, and you want to have a material that is clean enough so your Fermi energy is very close to Dirac point, so EF is very small. So these non-topological, non-Marana states occur at far away from zero energy. And only very few materials currently can have this kind of energy scale small enough on the milli-eV or 0.1, point a few bit less milli-eV or milli-eV like this materials. And what we believe also in this bulk topological insulator we have with a very, very high quality to allow this again, this is a necessary but not necessarily sufficient condition to prevent one of these common spalling states to mess up with the Marana states. And then if this is, and many other issues are solved, how do you prove you are measuring a non-binary anions, right? So people have developed protocols. One set protocol is to do the so-called, of course, you want to do the braiding, which is a bit more challenging, a little bit less challenging, it's believed, but still challenging, is to do some kind of fusion measurement. When you combine two Marana anions together, then it can merge and create a state which have either odd number of fermion, which is electron, or even number. It could just be 1 and 0. So this is called anion fusion rule, okay? And this experiment is one of the key, consistent to be one of the smoking gun evidence in the, besides the non-abelian statistics for these non-binary anions. Itself is a version of non-binary statistics, I should say. And one way to do these measurements is build, again, Josephson junction networks to do this kind of parity measurements and to build topological Josephson junction around topological insulator. So I quickly run through one example, I guess in a few minutes. You can build this Josephson junction on the topological insulators. There are many other, actually, there's many experiments done like this. These are some recent experiments done here at Purdue with a colleague, Leon Rockinson, in close collaboration and others, to explore these kinds of Josephson junction on good quality topological insulator I just described. And even though there's earlier Joule junction experiment done like this, but these experiment on clean topology shows a number of very interesting behavior. Not only you have good Joule junctions, they have unconventional behavior, critical current as function temperature, which we believe arise from the real space topology, meaning supercurrent really running on the surface. And most interestingly, this one example, which I highlight, the Joule junction, it turns out very interesting. The current is dependent on the phase or phase difference between these two superconductor contacts. And in this topological insulator junction, the dependence turns out to be highly non-sinusoidal, had this kind of very skewed fashion. For conventional Joule junction, like the aluminum oxide aluminum, or if this is some conventional metal, this behavior should be sinusoidal. So without going too much into detail, we believe this non-sinusoidal behavior is actually coming from the K-space topology, this spin helical nature. Therefore, the scattering from momentum to the optimum is forbidden. You have to reverse spin. So they give you a topological protection, can give you this non-skewed, non-sinusoidal current phase relationship. So I skip most of this. There, you can understand this in the Joule junction theory with some twist. It is also possible this arises from so-called topological Majorana fermion in the Joule junction, but it's spoiled by so-called quasi-particle poisoning. That can also give rise to these kind of skewed current phase relationship, which we cannot distinguish between these scenarios. Okay. Nonetheless, experimentally, I'm experimentalist. So the facts are, if you do measurements, so there's a technique to do this kind of measurement, build SQUID devices. SQUID is also a device important for qubit. But if you do this measurement, you observe this highly skewed current phase relationship, which could be due to these topological Majorana fermion Joule junction under quasi-particle poisoning that you switch between two different parity branch with the cusp. Here, right, this kind of behavior we see is non-sinusoidal, or more trivially, but not totally trivial, could be from a junction with a very good ballistic transport property. And here we believe protected by this forbidden scattering, because in the nanowire, where the topology is weakly destroyed, we recover these sinusoidal current phase relationship. But one of the interesting thing is if you have this unconventional current phase relationship in the Joule junction, so we have made an interesting new kind of Joule junction, which we believe topological protection, this case space at the very least, maybe Majorana plays some role, but we cannot claim that. There's two possibilities. But regardless of mechanism, these non-conventional current phase relationship is already quite interesting. There's actually various theoretical schemes you can take advantage of these high harmonic. If you have unconventional non-sinusoidal, your current phase can have these high harmonics other than the usual sign. You can actually, in principle, engineer junctions, take advantage of these degree of freedom to make more error resilient junction that cancel some of these noise. So this is already quite interesting to use topological insulator-based junction to protect qubits, so to speak, even without using the more exotic physics such as Majorana anions. Of course, if you get that, then even you can then use these braiding, all that to build topological qubit. So I think it's a material has this many aspect interesting properties, make it very interesting for potential quantum computing application. So again, the pathway is relatively clear, was described by many theories, how to build these junction network, braid these, if you have this fundamental material and device worked out at this level, and to fuse them, do fermion parity measurement. Some of that is very much of interest in the center toward this topological computing application. So I think I'm running out of time. I'm just saying, I won't say too much. I already say I probably only can talk about these two insulators. And this, I just say in this very last example, when you have a magnetic insulator with fluctuating spin in this quantum spin liquid, even though it's insulator, there's no charge degree freedom, but there's a lot of activity recently, for example, by couple them to a spin orbit coupled conductor, you can start a probe using other conductor in proximity coupling, probe their spin states, start to do transport measurements to reveal the spin configuration. I won't have time, but you can read this detail in the archive. But I end with this slide. Just in the last few months, maybe a year or so, there's lots of theoretical papers popping up, some of them from Quantum Science Center, proposing ideas, whether it's a coupling to superconductors or coupling to magnetism, like or spin orbit coupled material, like what we did in that archive paper, or doing thermal transport, try to actually build devices in the spin liquid insulator like this, start to manipulate and probe the signature of non-binary anion. I think this is very exciting, also emerging area research that it's fun to, we look forward to see some of these experiments realized in the coming years. So I will stop here. So I told you 3 insulators, and which I think are emerging quantum information materials that have very interesting physics and properties for future quantum technologies. If there's time, happy to answer questions.
All right. Thank you, Professor Yang Chang. Can we give a round of applause? Thank you. Any question from the audience? We got a question for a couple. We got time for a couple questions.
There's one there.
So just a fundamental question, can you summarize that what are the limitations of the current conventional materials that are used for quantum computing? And what is the properties of an ideal material for quantum computing? Is that clear?
I think I heard the question is, what is ideal material properties for quantum computing? Is that, yeah.
Can you summarize that what are the limitations of the current materials that are used or the conventional materials? And what are the properties of an ideal material for quantum computing?
Right. First of all, very much of this is actually unclear. We know at many levels, and also it depends on which kind of quantum computing platform you're talking about. Okay, I think Chris may talk about the things limiting ion trap quantum computing, which is their own set of issues. So you have to be specific. For example, in the superconducting-based qubits, right? For example, just talk about aluminum oxide, aluminum junction. There are a number of issues people already identified that is problematic. One of them is this defects in aluminum oxide. I talked about the 2-level defects, which give rise to fluctuation, even noise in the tunneling, for example. And even a very trivial thing, like a thickness being aluminum oxide is not perfectly uniform, that also causes problem. Okay, so it's hard to make a large number of qubits that behave exactly the same. That's actually a problem for scaling up. Other problem, like people also shown, even when you cool down this Josephson junction, there could be molecules absorbed on the surface superconductor, which if some of them carry magnetic moment, they can fluctuate at low temperature. That also causes decoherence. So that's for superconductor. For semiconductors, quantum dot, you may have a valley, uncontrolled valley, degree freedom in, say, in silicon or in gallium arsenide, nuclear spin fluctuating. So it's material, somewhat material specific, but it's generally coming from various material defects or non-uniformity of some degree of fluctuation or noise that we don't control. So the hope is to, so 2D material at the conceptual level give you this atomic control. In reality, it's also challenging, but give you a different degree of freedom. You can tune the material property. And so that's I think that's an answer to your question.
All right, thank you, Professor Chang. If you have any remaining question, we have that question forum. We can readdress them during the panel today. So again, Professor Yang Chang. Next, we have Professor Chris Monroe here. So as one of the world's leading experts in ion trapping for quantum applications and the director of Duke Quantum Center, Professor Chris Monroe is working to engineer a scalable, practical quantum computers through his work as the chief scientist at IonQ. His group focuses on the use of individual atoms and photons for fundamental studies of quantum physics and applications in quantum information science. A long-term goal of his research is the realization of large-scale quantum information networks that could store and process information in a way that would eclipse the performance of conventional computers.
Yeah. So, okay. Just need a number.
Yeah, here.
Okay. Do you want to join? Yeah, go ahead. I bet you do.
We will have a half-an-hour break after Professor Monroe's presentation.
You know, log out or something. Oh, there you go. can use this. All right. Hey, you're in.
You got HDMI into this.
Yep. Oh, it wasn't plugged in all the way. There it is. There you go.
Excellent.
All right, again, Professor Chris Monroe.
Thank you. Everybody hear me okay? Is this being amplified in the room or is it on for Zoom or both? Okay. Okay, thanks. Well, it's a pleasure to be here. Thank you, Sasha, Vlad, and others for hosting the event. My hour here, my lecture will be at a pretty high level. I want to talk about well, I will talk a little bit about atomic physics as a platform for quantum computing. I'll talk a little bit about engineering, but I want to sort of leave you with the impression that we're at an era in the field where there are small quantum computers out there, and we need people to use them. And what I mean by that is that it's an interesting field where we don't really have today, obviously, a killer application that everybody's deriving value for. But there are some platforms that we know how to scale. I don't want to say it's easy, but it is going to be straightforward. It's going to be very expensive. But as we scale these systems, they will become more powerful than what we can simulate on classical machines. That doesn't necessarily mean there will be applications that will derive value, but I find it hard to believe there won't. If you can't simulate what's going on in a programmable device, I think it will require some education, some people using these machines to learn what they're good for. Okay, so I want to, I'll be talking based on, of course, the work I've been doing for a long time in an academic context, and the platform we're building, trapped atomic ions, are now mature enough where there requires an industrial type approach to building these things up. And as I hate to say it, I'm a professor of physics, I'm a professor of engineering too, but engineering, the real task of engineering rarely happens at a university. The example I like to give is, would you fly in a helicopter that was built by a bunch of graduate students? I wouldn't. And it's because engineering is, I'm still trying to understand exactly what it is. It's very hard to put your finger on it, to make something reliable that a third party can use over and over again. And we're sort of getting into that stage in some of these areas. But I think academic physicists, chemists, scientists, and engineers, and those from all of the sciences, even social sciences, need to start to think about using these devices. Okay, so I recently moved to Duke University a couple years ago anyway, and I'll talk about a lot of the work there, as well as some of our adventures at IonQ, which is a company that makes full stack quantum computers based on atomic ions. So this is a summer school, so I do want to be pedagogical, at least for a moment. Many of you do this as you can fall asleep for a little while, but to me, the field of quantum computing is a wonderful combination of, I think, two of the pillars of 20th century thought. Quantum physics, which was largely esoteric in most walks of life, and information theory, which was not esoteric, and it was, of course, exploited to give us the information era in the last century. So these two men, Alan Turing and Claude Shannon, I think are owed a great deal of credit for their abstraction of information. Yeah, I like it that way, actually. Yeah. Okay, all right, good. Yeah, that's even better. So they both abstracted the idea of information. Turing, you probably know what a Turing machine is. It's an abstract type of computer. He even sort of devised what a machine would look like, having a bunch of bits on a memory, a tape or something, and this tape can fly across a head that has memory and has some nonlinearity going on. It has conditional operations. And with that kind of device, you can do any computation, turns out. It's a universal machine. Nobody's ever made a computer like this, really. But the mathematical model of those computers can always be mapped to this. So the idea of a computer without any hardware, this is not real hardware, it's abstract. And Shannon, of course, and his colleagues at Bell Labs invented information theory itself. They coined the bit, the binary digit, as a mathematical interpretation of what information is. And we recognize this, the Shannon information entropy, that has very close and subtle ties to thermodynamic entropy that we know very well in chemistry. This is a picture of some of the early vacuum tube computers that were stimulated by Shannon and Turing from the UK. They were actually first, the US here, and Soviet Union. So these are vacuum tube computers that had as their working elements these triodes, these vacuum tubes. Well, these are industrial vacuum tubes. You can make them, but they're not very reliable. They're vacuum tubes. They break a lot. I think these machines had many thousands of them, and they weren't too reliable. So in the spirit of what Turing and Shannon taught us, there's no need to be restricted to vacuum tubes. And indeed, in the 40s, we had the advent of the solid-state transistor. This is actually germanium. It's not silicon. And there's a thin gold foil on this dielectric here. And basically, it's a transistor. The current going through that's sort of tunneling through this little junction here can control a much larger current through the germanium. So this, to me, this actually looks much more reliable. These vacuum tubes compared to this. And this is a physics experiment. I mean, it looks like one. In fact, it was very unreliable. The temperature had to be right and so forth. Even the humidity in the room had to be tuned up. So at first glance, this didn't look like it was very promising. But it's solid state. And back then, there was very little technology to fabricate things like germanium or silicon. And of course, this is really what was behind Moore's law in the information era, the ability, well, to realize that you could indeed invent technologies. Cleanliness was among them, to be able to fabricate semiconductors en masse and put billions of them on a chip. So there's Moore's law. There are many different versions. This one scaled to 1978. It's the number of transistors on a typical CPU chip over the years. It's a log linear plot. So it's about a factor of 10 every decade. And we all know that Moore's law is this exponential growth. It's all on the same size CPU. The CPUs never really grew because it turned out the connections were the bottleneck, and it would be much harder to go over those distances, and the power dissipation, which is another version of Moore's law, I guess. But one thing to notice, of course, is that in the last few decades, the last decade anyway, this conventional version of Moore's law is starting to hit diminishing returns. One reason is that these transistors are getting so damn small that they're approaching the size of molecules, individual molecules. Wait a few years, it'll be individual atoms. So this won't go forever. And I don't think anybody claims that quantum computing is the answer to keep going along an exponential curve. But it's tempting to say that. We don't quite yet have all the infrastructure in place or the algorithms. But quantum computing does have an end run around Moore's law. And in fact, it was first realized remarkably in 1959. Feynman at an American Physical Society meeting, his speech was called "There's Plenty of Room at the Bottom." And he noted that I think he was inspired by this picture here, the solid state transistor. When you shrink them down to individual atom or molecule size, there are completely new opportunities for design. And he thought this way because the laws of physics, when you get to the very simple, are completely different. So that was quite a visionary statement, especially since he didn't know what those opportunities would be. He just had a good intuition there would be opportunities. And by now, I think everybody agrees that opportunity is indeed quantum computing. Okay, so I like to think of well, let me back up a little bit. Qubits are an extension of bits. I think you all know what they are. Quantum superpositions of 0 and 1 with a continuous variable that allows you to describe the weighting of 0 and 1. So it sort of has an analog aspect of it. Analog computers are not very stable. Noise tends to accumulate exponentially, which is something to keep your mind on. However, when you put lots of qubits together, you get exponentially many weightings you have to deal with, right? With 2 qubits, there are 4 possibilities. With 16 qubits, with 4 qubits, there are 16 possibilities. Every time you add a qubit, you double the number of weightings or amplitudes you need to describe the quantum state. So this is, in a sense, an exponential boom. And I like to think of what a quantum computer is. The next slide covers it entirely at a little bit of a high level and kind of vague. I think of it as good news, bad news, and good news. The first piece of good news is you put a bunch of qubits together, you get this exponential blow up. So a block diagram of maybe a 3-qubit quantum computer would have 8 states. There are 8 3-bit numbers. They all have content. So these A0 through A7 are the amplitudes of those 8 states. And this block diagram would be if you want to compute a function of 8 with 8 different inputs, you can do it simultaneously. You can do parallel processing with one device and one turn of the crank. Okay, 8's not very big. 300 is very big because 2 to the 300, you've probably seen this. This sounds overhyped, but it's very interesting. 2 to the 300 is, you could never have a classical computer in the universe that could have 2 to the 300 variables in it, because every atom of the universe would have to be part of that computer, and then some. You have to have leftover atoms for people to run it. So 2 to the 300 is a huge number, but 300 is not so big. So this is really where the opportunity is. It's huge. It's not just good news. It's amazing. There are problems out there that have configurations approach. Combinatorial optimization problems can have 10 to the 1,000 configurations. You would never solve those using a classical computer. And I will say the only way you will ever solve those is with a quantum computer or something even more powerful. There's just not enough space in the universe. Okay. Now, this seems overhyped saying that, and I'll get to the bad news in a minute. But some people sort of indict this already. Well, how do you can't control 2 to the 300 variables. You just said you can't store that in the universe. How do you expect to control them? Well, you don't really need to, in a sense, because entanglement keeps track of things. Let me give you an example. These 8 qubits, these 3 qubits with 8 states. If I flip the first bit from 0 to 1 and 1 to 0, what have I done? I've exchanged these top 4 amplitudes for the bottom 4. In other words, A4 and A0 swap, A1 and A5 swap, A2 and A6, A3 and A7 swap. So in fact, 4 swaps happen. If I had 300 qubits and I flip just the first bit, just one bit, that's a very innocent thing to do. Take that bit by itself, just flip it. Now, if it's generally entangled with all the other bits, you've flipped 299 amplitudes. So the structure of entanglement, in a sense, allows you to have this amazing amount of wiring that you could never do in a classical computer. So that might not be a satisfactory answer to many, but you don't need to keep track of lots of things. If you ever have to keep track of 2 to the 300 things, forget it. But if you have to keep track of only 300 things, or maybe 300 squared things, some small polynomial of 300, then I think there's hope. Okay, I haven't even gotten to the bad news. What's the bad news? The bad news, of course, if you do this massive parallel computation, you have to look at it. You have to measure it. And the one thing we learn in quantum physics To me, it's the weird thing of quantum physics is that when you make a quantum measurement on something, just the act of measuring it changes it. It collapses the wave function. If you don't like that type of interpretation, pick your own. It'll give the same answer. The wave function collapses. You get only one answer, and that answer is really random. The bigger the system, the more random it is. If we had 2 to the 300 inputs here, and we computed something in parallel, a table of logarithms or something, we got all those 2 to the 300 outputs. When we make a measurement, we only get one answer, and its probability is given by the square modulus of the individual amplitude corresponding to what we measured. But we have no idea what that means. We could have, we're flipping 300 coins here. So the answer, we'd have to know what input corresponded to that answer. We don't even know that. So this is really bad news. And in fact, I'm sure Feynman realized this in '59, that the quantum measurement destroys an obvious gain by having all this massive superposition. So the final piece of good news, and this actually didn't come out until the late 80s, early 90s by David Deutsch, among others, and that is that these amplitudes before measurement, they can be allowed to interfere in a very controlled way. And this is the art of the quantum algorithm. This is very hard to draw in a picture, right? We're opening up the black box here. Well, what's going on? These blue rays are supposed to denote some kind of a propagation in time from left to right. The red dots are called quantum logic gates. They're controlled interferences between amplitudes. I'm being a little bit vague, but we can use the language of gates, logic gates, Boolean logic from our classical computing knowledge and apply it to quantum. This red dot could be a controlled NOT gate. You flip one of the bits depending on the state of the other bit. It could be an AND gate, it could be an OR gate, it really doesn't matter. But the point is, these interferences, in some cases, can give an almost completely destructive interfering output, where all of the amplitudes at the end are 0 except for one of them. Now, this looks a lot like that, where we made a measurement, but no, there's no measurement here. There's no randomness. The structure of the gates, in a sense, it forces the quantum wave function to sort of amplify one of the states out of the zillions that are back there. Maybe it's not one, maybe it's 300 states, but it's not 2 to the 300. And if it's only 300 states, you could repeat it 300 times and get an idea for the distribution. And that distribution, or in the case of a single output, that single output could depend on all 2 to the 300 inputs. That's a quantum computation. And you'll note I'm being quite vague because there are not that many algorithms that sort of fit this mold. Okay, that's it. That's the final piece of good news. And the trick, of course, is that, well, we have to have a superposition that's not measured, meaning that it's super isolated from the environment. Otherwise, it doesn't mean that I'm measuring it, but it's not interacting with its environment. Otherwise, there are no new opportunities because it's not quantum. If you have even a quantum system, it interacts with an uncountable numbers of degree of freedom, it's no longer quantum. So you have to have an isolated system allowing you to do the computation in the dark, as it were. Then you have to, if that weren't bad enough, two worse things. You have to control the system and nudge it around without looking. You have to be able to control a quantum system without betraying its state. I think of this sort of like, if you want to think of a coin toss as a qubit, that analogy, because a coin is in a definite state at all times. If you imagine a coin in a black box, it's in a 75-25 state of 75 heads, 25 tails or something, whatever that means. If I want to flip the odds from 75-25 to 25-75 without measuring, I can just flip the box over. Okay, so it's that kind of operation. We need to manipulate quantum systems without getting information out. And then at the end of the day, we have to get the information out. We have to measure with very little noise. So having this gating of complete isolation to complete exposure to the environment, really hard. Not many physical systems fit the bill. So what are the applications? One of the best known algorithms that fits this mold is actually a very important one. It's factoring numbers. Number factorization is known to be it's believed, there are no known algorithms that make this easy. It scales exponentially hard with the number that you're trying to factor. Exponentially in the number of bits representing the number you're trying to factor. So 39 is easy. We memorize small numbers. This one's actually easy on a computer because that number is not big enough to challenge the power of your laptop. But if I give you a number with 1,000 digits, forget it. You can't factor it. And the cool thing about factoring is you can check. I'll talk about that a little bit later. Because if I've claimed to factor numbers, you can always make the number yourself and hide the factors. And you challenge me to factor it. If I can't factor it, I probably don't have a quantum computer. If I can factor it consistently, I probably have a quantum computer. Or I invented some classical algorithm. We always have to leave that out there. So this is the complexity of the best known classical algorithm. It scales exponentially with the number of bits, little n, to represent the number you're factoring. It's actually exponential in the cube root of the number of bits, but that's still bad. And Shor's algorithm, Peter Shor, I forgot to mention, he discovered this in the early 90s following Deutsch's acknowledgement that quantum interference can build computers. And it turns out to be almost cubic. Well, it's n squared log n, something like that, where n is the number of bits. So this is a big deal in mathematics circles. It changes the complexity of this problem, factoring. And as you probably know, factoring is very important for code breaking. The inability to factor big numbers is why messages are secure under most public key data encryption schemes. So here's Shor's algorithm. Of course, you can talk a few hours about how the algorithm works. And the key to Shor's algorithm is, what the hell are these gates? What are they doing? How many are there? Well, fortunately, there are not that many. There's only n squared of them. So it's a relatively easy problem. But if you want to factor the number 39, well, we need at least 6 qubits. And we're going to make a quantum state that stores, say, the first 39, an equal superposition of 1 through 39. Using 6 quantum bits, you can have a few more, I guess. And we're going to do gates, and these gates exist. There's a recipe to do this where the quantum state goes from this to this. So I once showed these slides at MIT a few months ago, and Peter Shor's in the front row. So this is Shor's algorithm. I was kind of embarrassed because it's a beautiful way. It's a beautiful description, and it's one of the cleanest. It is the cleanest quantum algorithm out there on how to arrive at the certain quantum gates to do this problem. And I sort of hit all the interesting stuff in this little quick slide there. And now when you make a measurement, you get one of the factors. That's basically how Shor's algorithm works. And the point is, going from here to here doesn't take so long. It scales favorably with the number, okay? Well, there are other algorithms that are less mathematically interesting to prove, because you can't prove them, but they're probably more widespread. And I usually use the word optimization as a catch-all for these things. Optimization problems are among those where there's one answer that depends on lots of inputs. And that's why they're hard. They generally require exponential resources. What's the tallest mountain peak in this landscape? Well, you can see it here because it's only it's a function of 2 variables. The altitude is a function of latitude and longitude, so you can just see it. Well, what if I give you a function with 10,000 variables and it's a nonlinear function? What's the optimum or the minimum? Well, those problems we can't do classically. We have to we have heuristics where we sort of take guesses and hope the landscape is pretty local and smooth and so forth. All kinds of assumptions there. But optimizers are everywhere. Jumping down here, we all know the logistics problem of the traveling salesman. What's the shortest path between n cities, visiting each city exactly once? Obviously, a very important problem for all kinds of things in life. This is a combinatorial optimization problem. It's NP hard. And actually, nobody thinks that a quantum computer can do this either. And the reason is there's so many paths that the gap between the best path and the next best path can be exponentially small in the number of cities. And therefore, there's an exponential overhead in the amount of time it would take to get there. It's kind of technical. However, classical solutions to this problem are also bad, and they're heuristics and they're guesses. It may be that a quantum solution is a better guess than a classical solution, and it's easy to test it. Always keep that in mind. You better be able to verify your quantum computation. If I found a better path than you can on all the Oak Ridge HPCs you plug together, and I can do it with a quantum computer better, you don't care why or what. I just showed you the better path. So quantum computers will probably be first used in heuristics like this, where we don't have rigorous proofs. So academics and mathematicians and computer scientists, they hate that because you can't prove heuristics. So we do see lots of academics that sort of poo-poo the whole field because they can't prove things about it. But you know, as I move into the experimental land here, there is an argument for just building it and see what these things can do. And so with that pedagogy, I want to now jump into the laboratory. What should we build these things out of? Clearly, it's a tall order. The coherence is extreme, and we need to, as I said, we need to shut off the system from the environment while we execute these gates, and then we need to turn on the environment to make these measurements. So this is adapted from this is 6 years ago. Science Magazine did a internal review by their editors of the field, and they listed a host of potential experimental systems. And these are all exotic in their own way. I grouped them, I modified this a little bit. I grouped the ones that are based mainly in solid state onto the right here. I call them synthetic qubits. These are emergent quantum degrees of freedom, very interesting, amazing condensed matter physics mostly behind most of these things, including the concept of superconductivity, which is truly amazing, just that phenomenon. Silicon spins, NV diamond, very interesting quantum dots, artificial and real, color centers. These are interesting systems. They typically have to be really cold to get rid of couplings to phonons and so forth. So that's okay. You can argue that's a technical issue. And you get these beautiful degrees of freedom in solid state systems that you can think about wiring up. I think there's still much to be done in this field, mostly in physics and engineering and surface science and chemistry and material science. And that's, I think, what Purdue is all about. I think that's that's a big deal here as one of the top flight quantum materials institutes in the country, if not the world. A lot of fundamental research done there. Now, what about these quantum bits on the left? I call them natural quantum bits. Why are they exotic? Well, when's the last time you saw a single atom isolated from its environment? Well, you don't usually see that. They're usually in a vacuum chamber. That's pretty exotic. They're isolated, but what's not exotic is the definition of the qubit itself. We're all comfortable with the concept of an atom. We don't manufacture atoms, they're given to us, and they're perfectly replicable. And I'm not exaggerating. They are perfectly replicable. If you have the same isotope of the same element, you can make them all identical. They're in fact atomic clocks, and for a good reason. Atomic clocks are supposed to be replicable to have the same energy splittings that define a time standard. So atoms, ions, individual photons, individual electrons, things like this, the natural qubits, these platforms on the left here have different challenges, but I would argue they're not physics challenges. We're not going to learn much more about the rubidium atom. Sorry to say. It's a pretty simple atom. It has some number of electrons, and there's spectroscopy. You can measure it to 20 digits, I guess, and there could be hidden, higher order quantum electrodynamic phenomena going on there. That's real physics for sure. But what we're talking, that's way better than what we need. We need like 10 digits, and the first 10 digits of any energy spacing in an atom, I argue there's not much physics there. You just have to measure. The challenge is almost entirely on the engineering side and the control side. How do you get a bunch of atoms together and hold on to them sufficiently well isolated so that you can do these gates? Okay. So what's exotic there is this is a kind of engineering that we haven't done yet. Nobody's really done. And I would argue that the challenges are way different over here on the left than they are on the right. They both have different opportunities. I think we heard in the previous talk the idea of having these topological emergent degrees of freedom. That's fascinating because it actually encodes an error correcting encoding in the structure of the system itself, which is just beautiful. There's just beautiful physics there. And I think what I love about this field as a physicist I would say at my core, I'm a physicist. I think there's going to be physics in this field for many, many decades to come. But there also needs to be engineering, and I am most involved with probably, I would argue, is the most mature platform where we can start engineering systems, and I want to talk about that now. So this is a collection of individual trapped ions, atomic ions. These ions are actually Uterbium 171 singly ionized, 171 ytterbium plus. Talk more about that in a minute. This is a chip. It's about this interposer here sticking up is about 1 centimeter across. It's called the HOA for high optical access. HOA trap made by Sandia National Laboratories. It's hard to see here, but this bow tie thing, this is a gold, there's about 100 electrodes here. They're plated with gold, but it's mostly silicon and silicon dioxide. It doesn't matter because there's nothing quantum about this chip at all. We run it at room temperature. It's just a place where we can do good machining at the micron scale, very simple. There's no nanometer scale, anything here, except at the atoms. The atoms are floating above this surface. Again, that notch you see is, I don't know, it's about 5 millimeters across. The atoms occupy about 1/10 of that. They're about 1/2 millimeter left to right, and they're 1/10 of a millimeter above the surface. So they're very close to the surface, but 1/10 of a millimeter is not that close. And the reason it's a bow tie is that we shine laser beams to skim the surface. They focus down to hit the atoms and then come out without hitting the sides. And these laser beams are our eyes and ears on everything. They allow us to initialize, read out, do gates, everything with these atoms. They are scattering light in this picture. Obviously, this picture was exploded and added to the picture of the trap that they're supported on. These are 80 atoms if you count them, and they're separated by about 5 microns each. It's not uniform, the separation. I'll talk about that in a minute. These blobs are diffraction limited spots. The atoms are laser cooled to be about 1,000 times smaller than those blobs, but they're nearly point sources, a few nanometers in space, and we can image them to about a micron due to the diffraction limit of our optics. The light's not blue, it's near ultraviolet at 370 nanometers for ytterbium. 370.xxx, it's actually 369, and I could give you the other 6 digits, I just don't know. Okay, so we're going to store a qubit, 1 qubit in each atom. When we turn the light off, the laser light, the atoms are still there, they're trapped electromagnetically. That's the purpose of these electrodes. So they're just sitting there. They can sit there for hours. They can sit there for months if you cool the chip to 4 Kelvin. They can sit there for months because it's about the vacuum level. When you have a 4K surface, the vacuum is much better. It has nothing to do with the temperature directly. It's just that with the ideal gas law, if you lower the temperature, you also lower the pressure. So it's a cheap way to get really low vacuum levels. So this thing is indeed in a vacuum chamber. So I think I've said enough about the chain here. Oh, the ion trap itself, you can tell it's very anisotropic. The axial dimension is much more weakly confined than the 2 radial dimensions by design so that they form a line. There's technical reasons why we want to do that. There are alternatives. Don't ask why we're not doing it in 2 dimensions. We don't need to because the Coulomb interaction is long range. Every ion talks to every other ion. Okay. Now the qubits themselves. So here's a little bit of atomic physics. Why 171 ytterbium? Well, turns out this atom is remarkably simple. You may not have guessed it. When you ionize it once, it has a single valence electron, and then it has about 70 other electrons that are in a closed shell. They're all paired off, their spins and otherwise. So it's just one outer electron, and that's the only electron we really touch. And the nucleus has 171 nucleons. It's like 72 protons, I think, and 101 neutrons, something like that. And all the spins are paired off except one. So it's a spin 1/2 nucleus. So when I think of ytterbium 171 plus, I think of hydrogen, neutral hydrogen. It's the simplest atom. The ground state's just an S. It has hyperfine structure, just like neutral hydrogen. These 2 levels, the 1, 1 and 1 minus 1, they have a Zeeman shift when you're in a weak magnetic field. But the qubit are in the M equals 0 states, which are magnetically insensitive to lowest order. These are sometimes called clock states. In fact, this is a darn good microwave clock, the hyperfine splitting in ytterbium. There have been atomic clocks made out of this exact system at a frequency of 12.6 gigahertz, and I could add a few more digits. I forget what they are, they don't matter. But when you make this atom, you get these sort of 11 digits for free. We know exactly what they are. We don't have to guess. Okay? And I say, when you leave these ions alone, you don't shine light on them, the coherence times, as long as you have the vacuum, sufficiently well. The coherence time is essentially infinite, as long as you want. So we don't have anything called T1 or T2 in our system. That said, we're going to be shooting lasers in to run gates, and I do want to talk about that for a little bit. I can see I'm going to rapidly run out of time, but in the spirit of a summer school, it's good. I'll leave some of the high-level stuff for later. What about measurement and initialization? How do we initialize a spin? Well, we do it through something called optical pumping, which is related to how we measure the spins. So I won't talk about optical pumping. We can prepare one of these two spin states with very high probability. Look in the 1960s for some Nobel Prizes, Casley and others on optical pumping. The measurement process is through optical scattering on resonance. So we go to the first excited state. Again, remember in hydrogen, the first excited state was P1/2. Same thing in ytterbium. This line is at 369 nanometers. And it turns out that if you're in this state here, I call it spin up, or you can call it 1 if you want 1, or spin up, down, spin down, or 0 is the other qubit state. If you're in this state here, we call it the bright state because it fluoresces. If you shine light at this wavelength, and you need other polarizations, that's just a detail, I won't talk about it, but it can only decay where it started from. It can't, there's a selection rule here that says this upper level cannot decay to here. And it doesn't. So this scatters light like crazy. And this is real data collected from a single atom where we gated the fluorescence for about 50 microseconds and we collected about 30 clicks. So we get a click every microsecond. And when we shine light on the atom prepared in the other state, it's 12 gigahertz off resonance. The line with the excited state, I forgot to mention, is 20 megahertz. Much smaller, than a million times smaller than 12 gigahertz. So when we shine light on an atom in this state, it's dark. It's as simple as that. Is it bright or dark? This is actually a real image of what we collect simply by putting the atom in one state or the other. The fact that these two distributions are so far separated means that we can, even in a single shot, this is obviously this data is a histogram of many experiments. We see an average 30, sometimes 40, sometimes 20, but we almost never see 0. And so the overlap between these two distributions is really small. It's so small that we have a near perfect measurement, perfect enough for some number of qubits. Okay, so that's the measurement. Sort of answers one of the real problems with our systems. When we turn on this laser light, we get a near perfect measurement. But you better not have that light running around while you're doing a computation. Right? That's the bad stuff. You don't want, and there's not enough black body radiation in the UV to cause any problem. So that's really in the noise. Now, how do we do gates? How do we flip qubits? How do we make superpositions? How do we do the controlled NOT gate? Well, we do this optically as well. We could do it with microwaves. We could do NMR, basically single effective spin NMR on these levels. But microwaves, the wavelength of 12 gigahertz is about a centimeter. And we have atoms that are confined to 0.5 millimeter. So it's very hard to control the microwaves to hit different atoms. So we use laser beams they have a precise beat note that matches this hyperfine splitting. How do we get these lasers? Oh, by the way, each laser is not on resonance. That's important. Very far detuned. And this is a very common technique in solid state optical systems as well. It's called Raman scattering, stimulated Raman scattering. It conserves energy. If we put two beams here at these two frequencies, it certainly conserves energy going from one to the other. And we have a very weak excitation, really small. We're not limited by that. Now, if you ask me why we use ytterbium of all atoms for our systems, it's because of this. Because the best wavelength to do this Raman scattering is at 355. And that is a commodity laser. You can buy as much power as 355 as you want. About $10,000 per watt. You can buy as much as you want. Just go to Livermore Lab and look at their nuclear ignition facility, NIF. It's at 351 actually, but who's counting? It wouldn't matter if you're at 351 or 355. This laser is made by Coherent, actually a branch of them in northern Germany. And the laser is used for lithography. For upper levels of CMOS optical lithography, 355 is a commodity. You have to use this laser without knowing what a laser is. It's a lamp. It has one adjustment, and it's the on switch. And this is why we love ytterbium, because we have these lasers. And better yet, it's a pulse laser. This gets a little technical. And the pulse laser naturally produces a frequency comb with just the right spectral components that we can use. We do have to control the frequency spacing. That's the rep rate of the laser, but we do control that. And that allows us to have the control we need to do gates. I've spent much of my career inside of a laser, usually in the morning and early afternoon. With this laser, you turn it on every day for years, and it works just great. That's a big deal. And it's starting to, you can start to see that we need to move toward that side of things, the engineering side, where we can start doing much more high level things. So how do these gates work? Okay, so the qubits are stored within the atoms. The atoms, they have a Coulomb interaction, but that's not the spin. The spins don't interact directly. It's the motion that interacts. So what we need to do is bridge that gap. We need to map a state of spin onto the motion. And then we can run gates. And this is a very quick version of how a generic ion trap quantum gate works. So let's say we want to entangle a pair of these two here. So we apply 2 laser beams that are focused to hit exactly 2 ions, the ones in question. Now, these laser beams are sometimes called optical tweezers. They exert a force. And due to the selection rules of this tuning and polarization, the direction of the force depends on the state of the qubit. And that's how we map spin to qubit state to motion. So a simple version of this is if the atom is spin up, it moves up. If it's spin down, it moves down. And so you can clearly see that just looking at these 2 ions and none of the others, and I'll comment on that in a minute. If you look at just these 2 ions, if they're in the same state, their Coulomb energy is exactly the same because they move together. But if they're in opposite states, if they're in the 2 odd parity states, they're a little further apart and they have an energy defect given by this expression here, which looks like a dipole, 1/r cubed, fall off with distance. These dipoles are big and they're sort of made experimentally. They're not natural dipoles of the atom, we make them. So if you had a superposition of up plus down in the atom goes in both places. Okay? Now, if you look at the 4 possibilities of those 2 qubits, only the odd parity states suffer this phase shift. Remember the Schrodinger equation, if you change the energy of a quantum system, that's a phase factor. But only up, down, and down, up get that phase factor, and it's the same, up, down, or down, up. And that makes this a nonlinear operation. Why? Because the product of what happens to up, down, and down, up is not the same as what happens to up, up. That makes it interesting. It allows you to get entanglement. You can make a controlled NOT gate out of this. If you set that phase equal to pi/2, you get what's known as the fully expressive controlled NOT gate. This was known for a long time. Serac and Zoller had a different version of this, but the Molmer-Sorensen version of it is sort of what I described. A couple of lies. Well, you always have to lie for clarity. It's not a true lie. It just allows you to sort of understand what goes on. Turns out these optical tweezer forces work in the x basis of spin, not z basis. But mathematically, that's the same thing. So in fact, our native 2-qubit operation is called an Ising gate, for the reason that the Hamiltonian is an XX operation. It's very expressive. It has a continuous parameter here that depends on time, or it depends on the spacing of the ions and so forth. So we have a whole family of gates here. Now, the other, and fidelity of these operations is very good. It is the best in any platform so far. It's about 3 nines now in some systems, and we know we can get to 4 or 5 nines. It's going to require serious engineering to get there. Now, the big, what I did throw under their carpet, importantly, is that these gates are relatively slow compared to the vibrational modes of the ion. So you should rightfully ask, what about all these other ions? If I push one ion around, it's like mass is connected by springs. They're all involved, and that's absolutely true. We have to keep track of all of those modes, and it's a little bit of a mess. But it's a classical mess. Put a bunch of pendulums connected by springs, that's a classical physics problem, and that's exactly what we have here. And as long as we know what those modes are doing, we're in good shape. Yeah, I just didn't have time to talk more about how we couple to these normal modes, but this is maybe not freshman physics, sophomore mechanics, where you take a bunch of masses connected by springs, not just nearest neighbor, Every mass is connected to every other mass by springs, but the problem is straightforward. You can find the normal modes, and then these tweezer forces, they drive the normal modes. You have to keep track of every normal mode and what it's doing. And in fact, by tuning a force away from resonance, in phase space, these normal modes undergo circles. What's phase space? Position momentum of a single harmonic oscillator. Like when you push a child on a swing and you're a little off resonance, they get excited to high amplitudes, and then you're out of phase and they come back. So they execute these big circles in phase space. Now, very recently, we've discovered, I want to talk about a very recent addendum to the family of gates we tend to use. So this is, say, a single mode of motion, position and momentum. You don't have to do circles. You could do squares by driving on resonance with different phases in the rotating frame. And then it turns out the entanglement is related to the area that you enclose in phase space. I could talk a whole hour on what I just said in the last 20 seconds. But the displacement operators in quantum optics are what we use to bring the state to back where it started, and we get entanglement. And it's important that you end up back where you started, because then you don't want the vibrations to be entangled with the qubits. Okay? It's sort of like a data bus, and you want to put information in the data bus and then take it back out and just leave entanglement. And it's easy to see if you do these 4 displacements in a loop, you get a phase factor in that displacement. It's like a Berry's phase, if you're familiar with that notion. And this is basically the same phase factor that I talked about is in the Ising gate. And you end up getting if you hit all the ions at the same time, you get a fully connected Ising coupling with a well-known matrix here, Jij. Now, turns out if you extend this to do, instead of a state-dependent force, again, this is a positive force, this is a negative force for the other spin state. If we make the force not state-dependent, but at each corner, we do a squeezing operator, which is, it's a sort of a parametric force. It's a different kind of force than a displacement. It's a squeeze, it's well known in quantum optics. But if we do this squeezing, anti-squeezing, squeezing, and anti-squeezing, you get these 8 operations. Okay, there's a displacement, squeeze, displacement, anti-squeeze, negative displacement, squeeze, negative other displacement, anti-squeeze. So 8 operations. When you condense these down, it turns out this phase factor acquires an exponential sensitivity to all of the spins. And in the end, you end up getting a many-body interaction gate. So it's not just a 2-body interaction. You can get a 4-body, you can get an n-body interaction. And that's sort of what was covered in this recent archival paper. We're working hard in the lab to demonstrate it. It's called a Toffoli gate, and it's a shortcut in many algorithms. And we sort of have that natively in the ion system. Okay, actually, here's a spectrum, turning back a little bit. Remember I said the ions are not equally spaced. Well, if you trap them in a harmonic axial potential, they aren't equally spaced because the ones in the middle feel the force not only from the trap, but from the other ions, all conspiring to squeeze in the middle. So the ones in the middle are closer together. Now, if you look at the spectrum of transverse modes, there are 2 n transverse modes. The axial is along this direction. There's the X modes and the Y modes. And we can use lasers to do Raman spectroscopy. And the detuning from the spin flip transition, we see these sidebands. This is the data on the bottom, and there are this is 32 ions. And so there's 64 peaks here, and red and blue are theory. We know where these are. It's just well, it's not analytic theory, but with 32 masses connected by springs, we know what the normal modes are, and we can see the features exactly where they should be, so forth. There's some reasons why this is not really what we want. One reason is that ions aren't equally spaced. And if we're going to have an optical tweezer array that hits individual ions, it's nice to have them equally spaced because probably your optics system is equally spaced. But also the modes are really close together. And you get sort of a mode forest here. You might worry, well, how do you isolate these modes here? They're so close to their neighbors. And that's absolutely true. Here is data on a near flat bottom potential. It's actually not flat bottom, it's quartic. But quartic is good enough. It gives you equal spacing for all the ions except sort of the end ones. Outside, this is 15. The central 13 are within 1% equal spaced, actually. So that's good for an optical system. But even a surprise for me, I guess we should have known this from theory, the modes are roughly equally spaced as well. This is very subtle. The reason that's really useful is that when we shine our laser beam to be detuned from these modes and we tune in between, like right here, we have a particular detuning from that mode and the same detuning from that mode. What's the detuning to the next mode? It's 3 times that detuning. That mode 5 times, 7 times, 9 times. All of the detunings are commensurate. And in phase space, all of the phase spaces close at the same time. That's it. It makes the laser very efficient at generating entanglement. It's a little bit of a side feature of having equally spaced ions. So the normal mode problem is not a severe one. We do have to in practice do laser pulse shaping to make sure all of these modes exactly cancel, but it works. It's sort of a calibration that we have to do ahead of time. Yeah, I really am running out of time, but I wanted to talk about one of the limitations. Why are you showing me 15? Why not 1,500 ions in a string? Well, the problem is, remember, we're focusing beams on individual atoms, and we had to make the trap very weak in that one dimension. The bigger the crystal, the weaker the confinement is, and the weaker the confinement, the more fuzzy the ions are axially. Now we're coupling to the transverse mode, the radial mode. That's what we're using as our quantum bus. But the axial fuzzing out basically means that we're going to sample noisy intensity. Okay, and this is just an example of an error syndrome that we have in our trapped ion system that is very technical, and it has nothing to do with the qubits themselves, but it has to do with having good lasers and better confinement of the ions. So if the ions are fuzzing out, they're going to sort of stochastically sample different intensities from our focus beam. And if you go through the math, it turns out this error scales in a very scary way, like the 6th power of the number of ions. So that would seem to be a kind of a no-go. If it goes like N6, you're in trouble after a while. Well, the good news is that N6 has a prefactor that depends on how fuzzy they are. And we actually know how to get rid of it. We're starting to get rid of it by doing something called sympathetic cooling. What does that mean? Laser cooling, I didn't talk about it at all. It gets the ions pretty well stationary. But when we're doing the gates, we can't do cooling. We can't do any dissipation while we're doing the gates. So when you directly laser cool a qubit ion, it will lose coherence because you're cooling it. You have to scatter light, and that will actually measure, that will leak information of the qubit state out to the real world. But if you trap different species of ions that can be used as refrigerant ions, coolant ions, that's called sympathetic cooling. You cool just that ion, and the others are cooled in sympathy, the other ones being the qubits. So what you would do is interrupt the computation as the ions fuzz out, stop, cool, and then continue. Stop, cool, and then continue. So this is actually, it is straightforward, and I won't go through you can, these slides should be recorded or something, so you can look up this paper by Marco Cetina, who's a young faculty member at Duke and a collaborator on how this error scales with wait time. The atoms are basically fuzzing out, and it corresponds very nicely to our theory. It's a classical theory. It's a pretty simple theory. And that's another thing to know about the trapped ion system. We know our error models. We can model them. We sort of understand them. I don't want to say there's no physics there, but we're not getting any new physics here. That's not the problem. And we know how to get out of it through sympathetic cooling. In fact, there's another proposal from David Alcock and Eric Hudson at UCLA and Oregon and other groups. It's called the OMG architecture. That stands for, obviously, optical metastable ground. But it's very cool. Yeah, so oh my God, it's really cool. And the point is, these ions, they have low-lying metastable states, like a D state. In hydrogen, the D state is almost degenerate with the P. But in ions, we have these low-lying D states that can only decay via quadrupole radiation, so they're really stable. If you park your qubit, this is energy vertically. If you park your qubit here, it will last for a good long time. In barium, 80 seconds. What you can do is decide, and what I'm getting at is the problem with multiple species of ions that you have to order them. You have to get things just right. And if there's a collision with the background gas, it rejiggers everything. Wouldn't it be better to do this in software? Let's have all the same atom, and we're going to say, okay, every 10th atom is going to be parked up here. You do that, and then you can do cooling on that transition, or the other way around. You can park your qubit here and do cooling down here. Whatever, you get to decide the functionality of every atom, but they're all the same isotope of the same elements. There's no reordering needed. If you do have a collision, things get rejiggered, you have to start over, but at least you don't have to, kind of wire your, system. It's almost like turning off your laptop and not just, taking every transistor out and having to repack them, okay? So this is very cool. It hasn't really been demonstrated in a system yet, but we're all looking forward to doing this. And the challenge is really, there's nothing, I don't see there's anything standing in the way of doing this. Well, except for this. I say except for this. This is one of my laboratories several years ago. Like any AMO laboratory, it's a mess. And I think I'm going to pivot very briefly into what IonQ is doing. This is the build over to that. Because back then, I'm sure Google and IBM and Intel, they sort of said, okay, those ion trap systems are kind of neat. They've been working on them for 2 decades. They have really clean gates. But look what they have in the laboratory. It's a mess. And well, this is a physics laboratory. And when you do physics experiments, you want flexibility on everything. Every mirror mount, this is largely an optical experiment, of course, and every mirror mount has 3 knobs. And so, you don't freeze anything. The good news is if you know what you want to do, you can freeze things. And without much exaggeration, we put all of this stuff here into a box. It's a couple of meters cubed. Some of the lasers are not in a box, but they're fed by fibers, so they're pretty easy to deal with. And Debo, you should stand up. You work on this one here. So if you have questions on that system, he knows all about it. Now, this is odd to have such a well-engineered system in a university, and it was afforded by very large efforts from IARPA and also NSF STAC, and more lately, the DOE Quantum Systems Accelerator run by LBL at Berkeley. And allowed us, the IARPA grant was a 5-year, $32 million program. Just me, Jungsang Kim, and Ken Brown, really. Most of it went into building this. A lot of that money goes right out the door. It goes to places like, well, Sandia is supported on the side, but it goes to companies to build optical systems, subcomponents that we can integrate. We went to L3 Harris and said, boy, we love your 32-channel AOM. You make it for CMOS lithography. Could you make a special model for us, for ion traps? And they said, oh yeah, sure, but it's going to cost you. And it's very expensive. But if you can justify it, some agencies are happy to go down that road, So that's, this experiment, physics experiment, is starting to look like a system. And if you look inside that system, I hinted at this, the guts of it is a 32-channel AOM so we have 32 beams. We can hold 80 ions. I showed you that, but we control up to 32 of them. Each beam actually is controlled by an RF input. So we need a pretty fast and agile and deep AWG times 32. So that's tricky, not impossible. They exist. RF system on chips, RF SoCs are now coming out that are making this a commodity. So things are moving well. But the guts is pretty simple. It's a lot of optics though, and it's not even integrated on the chip. This is all mostly free space optics. So we can still do a lot better. But when we built this system and its precursor, we first got an idea of the quantum computer stack. I've spent most of my life at the very bottom of the stack here. At the top are applications, algorithms, and in between is all the very fun stuff that we're starting to do. These control systems. How do you compile things? This is going to take a minute. I want to go through it. It's a fancy animation showing how laser beams. This is basically a quantum computation on a string of ions. The circuit's written up there, and here's what it looks like. I'm just going to pass on, but what is important is that we've had many folks approach us wanting to run circuits on our research system, and it's just exploding over the last few years. Institutes all over the place, government labs, other universities, even industry, and a lot of publications are coming from it. We're starting to play around with the system. And I'm running away. I won't talk about this at all. Oh, I won't talk about black holes. I love that one. I knew nothing about black holes in cosmology, but apparently scrambling is an important process in those things. And this circuit tests whether a particular unitary scrambles or not. And scrambling is thought to be important in a black hole. Now, with 3 qubits, It's pretty small and trivial. But Lenny Susskind at Stanford says that if we can do this with 50 qubits, we might be able to find emergent phases that you might expect in cosmological contexts. And there's a picture of a real pair of black holes and a real wormhole in between them. But actually, what I can't help but say, and you probably, many of you know more than me about this, there apparently is a connection between entanglement and traversing a wormhole. There are theories that bring those two together. So the big picture here is this is very high level physics in this case. It has nothing to do with atomic physics. Nothing to do with our device. And this is what I find just fascinating about all these collaborations over the last few years. We're learning all kinds of high level physics. And I want to give one more example before concluding, because there's some local interest there. Sorry. There's IonQ. Yeah, IonQ systems are on the cloud. I wanted to talk a little bit about IonQ. You can talk to me afterward if you want. But they're really, they've been doing some molecular variational quantum eigensolver applications. And I bring that to your attention, well, a couple of reasons. I sort of built up to it because it turns out very early work that kind of prefaced using quantum computers to do molecular simulations was started here. I remember, I think when Savory, when you first contacted me 20 years ago, I didn't know what the hell you were talking about. I didn't. But the idea of entanglement being why, the concept of entanglement in a molecule is why it's hard to simulate. It's a many-body problem. And it made sense that when you build a computer, you might be able to simulate that. And that's a big deal now. Now, this slide I wanted to show, and then I'll pretty much quit. But the popular way to do a quantum chemistry simulation these days is to do a so-called variational optimization. And what that means is you take a guess at the ground state of an electron that's mapped onto qubits, and you move things around just a little bit, and then evaluate the energy. Did it get lower? If it got lower, then that's a better configuration. You're looking for the lowest energy state. So you need to make a quantum entangled state and then change the energy just a little bit, and you're going to need to do this a lot. This is a controlled NOT gate between two qubits and a small rotation by d theta of one of the qubits. Now, this is a very expensive thing to do. You need two fully entangling gates and then a rotation. Now, rotations are cheap. Not only are they fast, but they're very high fidelity. We would rather do big rotations than small CNOT gates. Well, Ken Brown at Duke, he realized that this is the same as this. So here we have 4 full rotations by pi/2, but those are cheap. And then we have a tiny bit of icing interaction. This was huge for us. It divides by about a factor of 10 the number of gates that you need to run a VQE. And it's because our quantum gates are very expressive. We don't just have a C0 gate, we have fractional powers of C0, if you will. And there are other versions of that. So it pays, if you're going to run algorithms, don't ever be hardware agnostic. Dive all the way down and find out what the hardware can do. And if it can't, find a different hardware. You're never going to get anywhere being hardware agnostic. I hope in 10 or 15 years, you can be hardware agnostic, like we are with our cameras, you know, right? Memory is super cheap, so we burn memory by taking stupid pictures. Maybe qubits will be that day one day. So yeah, I'm so sorry I had to move so fast, but we have very direct plans to scale, including optical, going off chip to another, you know, I did have a small kind of schematic of that. You can have non-local entanglement through the sharing of photons. It's slower, but this is something that will allow us to build a modular system in the long run. And IonQ is going to go whole hog at that type of a scaling. And you know, the systems are getting smaller. Eventually, we're going to have the entire system on the chip. We're not there. Lincoln Labs and Sandia, other groups, NIST and ETH Zurich are making great gains on having optical fibers being supplied right to the chip. And this is great because the atoms are tied to the chip. Wouldn't it be great to tie all your optics to the same chip? And then when a train goes by, the whole thing vibrates all together. Everything's common mode. Right now we have free space optics. It's big. It's a meter cubed. And we still are, even though it's the best system out there, there's still sort of, we're suffering noise issues there. And so as we build our system, the number of qubits, we also have to do more gate operations. So this is tricky. As you add more qubits, they have to be better qubits. You can't add more qubits and make them worse. Otherwise, you're going to go up in this direction. You're never going to cross that line where you can't simulate something. And by the way, factoring in interesting numbers way out in the distance. So don't worry about that right now. I wanted to make one very brief comment. This is pretty much my last slide. And that is, there's indeed quite a bit of hype in the field that it will be a panacea for all computing, maybe someday. But we all worry that there will be this is the so-called hype cycle, expectations over time. And if you overhype things, interest could really go down the tube, so nobody wants to invest anymore. But we should all keep in mind that there is something to this field, and there is an ultimate slope going forward. And I think using these systems for scientific use cases like cosmology, nobody's going to pay. No company is going to be founded based on understanding how a wormhole works. Not now. But good science comes from that. And that could help pay the bills to tide us over until the systems reach maturity where they will hit commercial use. And as Purdue is one of many, they're sort of making a quantum science center that's not exactly university, it's not exactly industry, it's something in between. By partnering with DOE or DoD labs, this is something I think the government can play a big role in helping. And I guess as my last word, I don't think people should be afraid to pick a winner and go with it. If it turns out to be a loser in the long run, then move to something else. But you can't, that first picture I showed of the solid state transistor, that was germanium. It wasn't silicon. Why do we pick silicon? Many of you know the history more than I do. It's not the best semiconductor. Didn't have the best mobilities. We learned how to make it really good. There are all kinds of attacks on silicon over the years. They never panned out because we stayed with one path and we could do these kind of full stack integration of silicon and VLSI. It all happened because we decided to pick a winner. Shouldn't be afraid of that. So at Duke, we're forming a user facility type quantum center where we're building systems. They happen to be based on trapped ions to start with, maybe not in 10 years though. We're using these systems to understand quantum computer science, to understand how to compile a circuit, to do engineering of pulse control, and to do applications that are maybe outside of our comfort zone. And we have lots of young people, luminaries in quantum error correction like Robert Calderbank, CSS, he's the C, CSS codes. And we have engineering, physics, chemistry, lots of different departments there. And I think Purdue is going to do a very similar thing. I think the engineering and physics here is kind of latched, unlike many places. And I think that's a great thing. So that's all I have. Thank you. Sorry for running out of time.
Thank you, Professor Monroe. Any immediate questions from the audience? All right, if not, if you have more questions, we will have a panel again with all the speakers from today. And let's take a 20-some minutes break and come back around, what is it, 3:20? 3:20.
Yeah, that's my girls, yeah. 8 and 10. Саша, может быть, слишком много пуговичек расстегнут, нет?
Some people actually come
Больше
in
нет?
public and they wear a tie when they give a talk.
I'm not that started, but also I usually don't bring my host.
Should I bring a tie on Tuesday?
No. No, you look great, actually. And I mean, it's your style. Overall, it's a great style, cowboy style. And if you feel comfortable.
Remember, I lived in Texas for a while, right?
Oh,
So I wanted to buy you have the belt buckle that says gear what?
Hi, folks. Please return to your seat. We'll get started in 1 minute. All right, folks, we'll get started here. If you can get back to your seat, please. So next up, we have Professor Vladimir Shalaev. Professor Shalaev is the Robert and M. Burnett Distinguished Professor of Electrical and Computer Engineering and serves as the Scientific Director for Nanophotonics at Purdue University's Berk Nanotechnology Center. Professor Shalaev is the world leader in nanophotonics, plasmonics, and optical metamaterials. Being the 10th most cited optics researcher in the world with an H index of 110, his group focuses on quantum photonics, machine learning, nanolasers, and novel optical metasurfaces. And without further ado, here's Professor Shalaev.
Is the mic on? Yeah. Well, welcome again to this workshop. I think this workshop is kind of unique. It beats records in terms of variety in both age scale, starting from 8, Michelle, wave is your hand, up to, I would not say how far it goes. And in terms of geographical diversity, it's actually amazing that there was a guy who is called Frank Jr. He just, through chat, sent email that I'm enjoying this workshop sitting in Cameroon. So that's good. Okay, so what I'm gonna talk here about is how technology evolution, quantum technology evolution, which probably nobody argue is a reality now, could benefit from yet another technology evolution in AI, and also from the fields which I have been working quite for a while, metamaterials and plasmonics. I believe that some ideas from that are very productive and fruitful area could be applicable to quantum and enable things which might be otherwise not possible. So here is the outlook, and I guess 3 major messages I'd like to deliver today. Number one, plasmonics or plasmonic metamaterial enable confinement of electromagnetic modes down to few nanometers only. And this is the only way actually to beat the diffraction limit to that extent. And by doing so, you could actually enable dramatic per-cell enhancement and speed up to the extent that quantum processes happen faster than quantum decoherence. And that's the way to outpace decoherence and make it basically immune to decoherence, quantum processes. So this is message number one. Number two is, since in quantum photonics, and that's of course the focus of my presentation, we are dealing with exceptionally small signals, then you would benefit dramatically from machine learning approaches, particularly if you're talking about quantum photonic circuitry with thousands of elements. It's basically not possible to do it without AI. And that's the opportunity to take advantage from yet another parallel technology revolution going in the virtual as opposed to physical domain. And message number three is that with our recent discovery in our group of this quite efficient single photon sources in silicon nitride, there is a chance that this technologically important material platform could be used for quantum photonic circuitry and enable quite complicated system. All right, so this is like an introductory slide which shows how the number of calculations per second per $100 evolved with time, started from a simple analytical machine going to non-electronics-based computing. And the next speed up, I guess by now nobody would agree, would be related to optics and quantum, maybe both, maybe interplay between the poles. Because that's in principle enable higher speeds and larger broad bandwidths. So I already advertised that plasmonics expected to play a very important role. And so, and that enables really a very strong confinement, and I will show why it's so important. If you take, for example, this small metallic particles and somehow displace electrons, as it's shown here, clearly you have restoring force, electrons would start bounce up and down, and the confinement of this electromagnetic mode would be confined to the size of the particle, which could be as small as 10 nanometers. And if you take, let's say, so-called gap plasmas, when you have two metallic structures, let's say the silver nanocube and epitaxial silver field, and if you place in between your qubit, or let's say single photonimeter, then it would experience confinement which would be dictated by the size of the gap. And the size of the gap could be quite small, down to 1 nanometer. For example, if you use as your quantum system, HBN or other van der Waals type of material. So that's quite an interesting opportunity, but historically, it turns out that these ideas of plasmonics were developed initially for much stronger actually systems, random composite systems like those shown in these pictures. And I actually enjoyed working in these fields quite for a while before Eli Blanovich approached me and said, Vlad, this seems to be really nice physics, but it's random. People don't like random. Why don't you start working on something more ordered? But anyway, so these random composites quite often actually have scale invariant or fractal structure. Like you could see, for example, for this fern, you could see that the structure of the whole is repeats itself on the smaller and smaller scale. On this scale, then on even smaller scale, and so on. This is deterministically ordered fractal structure. So you really could have the exact reproduction of the structure. And this is an example of statistical fractal structure, which basically is aggregate of 10 nanometer size silver colloidal particles. And if you do a little bit mathematics, you could show that it actually satisfies this equation. Number of particles increases as the size of this structure to the power d, where d is the fractal of Hausdorff dimension. And as we showed in our early papers, it turns out that the fractal morphology promotes localization of collective excitations. clearly, if you have aggregate like this and excite with light, this plasmon excitation in single particles, they couple to each other and form collective modes. But because of this fractal morphology, actually these modes are localized in very small areas, which we refer to as hotspots. And in these hotspots, you have quite significantly increased local field intensity by several orders of magnitude, enabling dramatically enhanced nonlinear responses and many other interesting things. The amazing thing about this type of random composites, that their structure, their properties are defined by structure and by geometry, rather than by material properties of what they're built from, like silver or whatever. And that's exactly the same what happens for later developed metamaterials. And in that regard, these random composites actually served as precursors for metamaterials. And even people who worked on random composites like myself, John Penry, Kostas Sakoulis, we all worked previously in that field, then moved to the field of metamaterials, not accidentally. And speaking of these metamaterials, this of course is a wonderful way to design and engineer your physical properties, like in our case, optical properties, by basically controlling the shape and the structure of your material, your composite. In this case, we call it metamaterial. Meta, of course, in Greek means beyond. We create materials that have properties going beyond those which you can get with materials existing in nature. And I just flesh out here these good examples of metamaterial accomplishments, particularly when it comes down to so-called metasurfaces, which is 2D version of metamaterials. It's actually enable things as flat optics, basically basic optical devices like a lens, like a hologram, but much thinner than conventional bulk optics. Because in this case, you accumulate the needed phase, not through propagation of your bulk material, by abruptly changing the phase when light couples to these non-antennas, which are often plasmonic non-antennas. And as I mentioned, you could have this really very thin nanolens, metal lens, or in this case, it's meta hologram. It's actually still record thin, 30 nanometers thick only hologram. And it could actually also create something which one could argue holy grail of nanophotonics, non-reciprocal elements. All right, let's try to move to quantum and see how this field could benefit perhaps from what we learned in the case of metamaterials. Well, this plot shows that when it comes down to material platforms, it's actually big questions. And as Chris just mentioned, showing this table, they all have their pros and cons. And clearly there is a trade-off between interaction strength, where superconducting qubits seem to have a better control, and coherence time, where actually photons probably have the best possible protection. And of course, in between, we have all these different very promising material platforms, including atoms or their version ions. It's really, truly remarkable progress in that area indeed. And color centers and other approaches. But regardless of this, if you think in general of quantum, it's hard to argue that photonics would play an essential role there. And of course, we already have many examples of applications of photonics in quantum. Quantum communication, including this quite spectacular result when they enable this quantum communication through satellite, this Chinese group. Quantum sensing, quantum information, quantum simulation, and quantum computing as well. So we already know that companies like PsiQuantum or Xanadu, they're working on photonic-based quantum computing. However, if you look at what has been demonstrated so far, for example, this quantum communication I mentioned, the rate with which this machine works is actually quite low. It's kilohertz. It's not what you expect for optics. Optics designed to provide really high speeds. And the problem related to this, the reason why it happens, it's basically the same reason why photons are so robust. They're robust because they don't couple to each other. They don't have charges. And they don't couple much to matter, but for a simple reason that the size of the wavelength is so much larger than the size of atom or your qubit. So coupling is small. So and therefore, they actually provide this protection. Therefore, they're so robust. However, for many applications, if you would like to generate photons, you would like control to switch them, you actually need this strong light matter coupling. So ideally, you would like to have a situation when you have the strong light matter coupling on demand, where you need to create and manipulate photons. But when you send you information for large distance, of course, you would like to take advantage of the fact that photons are robust. And that's actually exactly the area where plasmonics could come into the game. Let me first show this simple example. This is an experiment we did with York Lloyd-Holt in ETH, and that's plasmonic modulator, which shows quite amazing actually speed. And that's what I'm actually after, that plasmonics enables really high speeds. So it's very simple. You have your signal going through this silicon waveguide. And when on its way, we have this gold ring resonator. And in this cavity, we place electro-optic organic material, which changes its refractive index when you apply voltage. And if refractive index is such that this mode doesn't couple to this ring resonator, then it simply goes through without any losses. However, if you apply voltage, change the refractive index, and the mode does couple to this ring resonator, then actually light doesn't go through. So you have this modulation. And the key thing, first of all, it's a very strong modulation, it's 10 dB extinction ratio, but the key thing is speed. So this thing operates at terahertz rates. And that's what I'm after. That's what you could accomplish with plasmonics. This perhaps slide is the most important for message in terms of what I'm here to present. That's about Purcell enhancement. I mentioned that there is this fundamental problem that photons don't couple much to qubits or, let's say, two-level atoms, whatever you have in mind, simply because the wavelength, simply because of the size mismatch. Wavelength is much larger than the size of atom. And we know the way to increase this coupling. We place your qubit inside of a cavity so that light would bounce many times between mirrors, go through your atomic system many times, and that, of course, effectively increases interaction. But you pay the price. So this Purcell enhancement, which I'm describing, goes as the ratio of quality factor of your cavity and the volume where electromagnetic mode is localized. Of course, for this system, for a cavity, optical cavity, volume is limited by the diffraction limit, lambda cube, the smallest. Whereas Q could be exceptionally high. For example, if you use a cavity based on a diffracting in photonic crystals, Q could be as high as 10 to the 8. So you really get enormously large enhancement in this case, but the higher the Q, the slower the response. So if you would like to make your system operate at high speeds, you don't want to deal with high quality factor. So how to get the way around? How still to get enhancement of your light matter coupling without slowing down the process? And that's exactly where plasmonics comes into the game, because in this case, we know that the volume where electromagnetic mode could be localized could be as small as 5 nanometer. So 5 nanometer compared to the visible is 100 times smaller. So you should take the third power, which gives you million factor enhancement. And quality factor for plasmonics is not that large, it's 100. So altogether you get 10 to the 8, something similar what you have in the case of this conventional approach with dielectric-based cavities. So, but in this case, the speed remains very high, because if Q is 100, it basically means that the spectral width of your response would be terahertz. The central frequency is 10 to the 15, so Q is 100, meaning that you move to terahertz spectral range, but it means that your system operates at terahertz speeds. And that's actually could be very advantageous, because at this speed, you could overcome the rate with which decoherence occurs. So to illustrate this point further, let me show this traditional approach to deal with decoherence based on high control of your system, which basically increases the coherence time. So by trapping atoms, ions, by going to very low pressures, you increase the coherence time. And of course, it's a very valuable and right way to go. But what if, in addition, let's say, or complement this approach, we simply speed up the process, make it faster? For example, what if, let's say, if you would like to obtain single photon source, or ideally a source of indistinguishable photons, which is a key thing for, let's say, photonic-based quantum computing. So to get many sources of indistinguishable photons, that's exactly what you need to enable all this computation and simulation. So if I speed up the rate with which my photons are emitted to the extent that the emission happens before the decoherence, then my system would be immune to decoherence. So that's yet another complementary approach. Simply speed up the rate with which your quantum system operates to terahertz rates. And that's what plasmonics can do. It could enable these speeds at the terahertz scale by simply confining electromagnetic modes to nanoscale areas, which you cannot do with dielectric structures. So let me illustrate this idea with some initial experiments we did. This is already a relatively old experiment, but at least it shows the promise of this approach. So what we have in this case, it's a epitaxial silver film of exceptionally good quality, I should say, and a single crystal silver cube. And in between, we place nanodiamond, 25 nanometer in this case in size, with nitrogen vacancies, which serves as a source of single photon emission. So it basically works as nanopatch antenna. So what you want from this antenna is two things. One, you would like actually to have the gap as small as possible, because the smaller the gap, the stronger confinement, the higher per cell enhancement. In that regard, nitrogen vacancy nanodiamond might be not the best thing, but HBN, for example, which is atomically thin, could be a better source of single photons. But at least this is one, small gap, as small as possible. Volume becomes exceptionally small, per cell increases dramatically. But another very important thing is you need to outcouple these photons at the rate which would be decoherence, as I pointed out, but also losses, the rate with which loss of plasmons occurs. And it turns out that it's possible. The size of the cube should be, let's say, reasonably large. So to say, it's like 60 nanometers or so, 50 to 100 nanometers. And it turns out if the size of the cube of that range, it would outcouple photons at the rate faster than decoherence or even loss of plasmons. So that's the idea. This is first experiments we did a while ago. It was simple-minded. We just randomly distribute nanodiamonds on top of this epitaxial silver, and then randomly distribute these silver cubes. And just by chance, in some cases, you find out the situation when a cube is sitting on the top of nanodiamond. And once we obtain that, yes, it is a single photon source, you simply measure this G2 function. It does go below 0.5, and it is single photon source. But when you compare it to the case when your nanodiamonds on glass to the case when they're sitting in this nanopatch antenna, so it was like 100 times increase in the rate of spontaneous emission. And the number of detected single photons also increased by roughly the same factor, 100, which means all this increase goes to radiation channel rather non-radiation one. But if you now take into account that the transmittance of your optical system is 25%, the collection efficiency is 50%, and the efficiency of photodetector is 75%, that the total rate with which number of single photons produced is actually quite high. It's 500 million single photon per source at room temperature. That's actually quite amazing. So, but it's not optimized how you could do it better, more precisely. And that experiment, which was done, Oksana Makarova, who actually was undergraduate student at the time. Now she is a graduate student with Misha Lukin, but she did this really remarkable work. So you would first characterize these nanodiamonds, how good they are single photon sources with nitrogen vacancies on glass. Then you pick up those nanodiamond, which looked really well, and place it on the epitaxial silver. Then the tip of this AFM, you push this cube at top of this nanodiamond. So this nanodiamond sits exactly at the edge of this cube, where the per cell enhancement, as calculation shows, is the highest. And then you obtain actually quite dramatic lifetime shortening, around 3,500, which results in record fast decay rate for a single nitrogen vacancy center, around 23 picosecond. When we did a little bit theory and calculation together with Jacob Kurdin from Johns Hopkins, we actually showed that under optimum conditions, when the size of this gap around, let's say, 3 nanometer, and the size of this antenna is like 60 nanometers, the rate with which single photon would be produced is 300 terahertz. That's enormously high rate. And the efficiency, radiation efficiency, would be as high as 96%. That's simply because it happens so fast that it's immune to any type of decoherence or losses in the system. So for specifically nitrogen vacancy, we are not there yet. We cannot produce indistinguishable photons because in nitrogen vacancy, the decoherence is crazy because of very strong interaction to phonons. It's actually like 0.01 picosecond, whereas the enhancement we obtain around thousands actually still would bring us only to, let's say, several picoseconds. So clearly we need to get a better, let's say, with longer coherence time single photon emitter. And then this type of per cell enhancement, we should be able to beat the decoherence rate. And that means that we would have this source of indistinguishable photons at room temperature, which would be a very important development for quantum photonics at room temperature. Okay, I already mentioned that machine learning, we expect play quite significant role. That was a guess in the beginning. We started to work on that, so we're pretty much amazed. So like, no matter what you touch with machine learning, really provides truly dramatic improvement in terms of measurement and many precision and many other things. So since I was talking about these single photon sources, let me illustrate what kind of difference machine learning could do for single photon, for characterization of single photon sources. So in this case, you have these nanodiamonds distributed on a glass substrate, and this is just like basically you see photoluminescence coming from these different centers. And when you characterize these centers, you need to look at their quantum purity, which is basically G2, how small is G2, correlation function. You need to look at stability, brightness, and if you're after indistinguishability, then you have to do additional measurements. But the point is, if you would like to have really small emitters, like let's say 25 nanometers, only 1 out of 1,000 would have single nitrogen vacancy. Others would be empty, no centers. So clearly it takes forever to find out, let's say, many good quantum emitters. Let's say if I would like to build a circuitry with 1,000 quantum emitters, that would take forever. So in the question whether machine learning could help us in terms of fast characterization of single photon emitters. Let me first remind how we characterize it. We have this correlation card with light pulses going through different arms, and you measure this G2 function as the function of delay between these two pulses. And usually to obtain a spectrum like this, it takes several minutes. Then you fit it with this Levenberg-Marquardt function, and you take this correlation function at 0 delay between the two pulses. And normally we say if it's below 0.5, this is single photon emitter. Actually, the smaller G2, the higher quantum purity. But if I would like to make it faster, if my collection time instead of just 1 second, that's the way the spectrum looks like. Of course, you cannot fit this type of spectrum with this type of function. So, but what you could do is instead, you use this machine learning training. So you first pre-characterize your single photon emitters. You do know that this is, let's say, single photon, this is not single photon, but just by doing this fit with Levenberg-Marquardt function, it takes a while, but then you know that you have, let's say, 50 or so samples to train with. And then you train your neural network by doing this 1 second collection time. And after you train it with very high efficiency, fidelity, you could actually say whether it's a single photon source or not by doing this 1 second measurement. And that's what is shown here. Let's say if I don't have this training of my neural network and do this 1 second collection time, then the accuracy with which I predict whether it's a single photon source or not is 50%, which means it's random guess because it's either single or not single. 50% means basically it doesn't work. Whereas I do use this training of neural network, then it's above 90%. Clearly, you do it much faster. Instead of minutes, you do it within 1 second, and the fidelity is quite high. If you look at all other metrics people typically use, they're quite good. So you really have high fidelity in terms of classifying your sources as single or not single photon sources. And speed up, it's close to 2 orders of magnitude. So let me illustrate, give you a couple more examples of this machine learning. So first, the second one is actually this based on super resolution imaging. But speaking of super resolution, let me remind you why we have this super resolution. Because the resolution limit, so-called diffraction limit, lambda over 2 numerical aperture, is actually comes from linear optics. So if you break, and there are also some other assumptions, and they're listed here. Linear optics, the sample should be stationary, illumination should be homogeneous, and you're supposed to use classical fields. In fact, if you break any of this, then you could obtain the super resolution. And to illustrate this point, let me just remind you that, for example, if I use nonlinear optics, such as stimulated emission depletion or stat microscopy, what Stefan Held developed, that would beat diffraction limit quite significantly. If you use non-stationary sample, you also could be diffraction limit, and that the basis for this stochastic optical reconstruction microscopy or STORM. If you use inhomogeneous illumination, as opposed to this, then you also can beat the diffraction limit, and that in the base defines the structural illuminated microscopy scene. So what if, could we get some advantage if you switch from classical field to quantum fields? An idea actually is known, and it was suggested in this debunking experiment by Stefan Held. So who said, hey, let's imagine that we have a source of photons that every time it emits, it emits only 2 photons every single time. Never 1, never 3, only 2. So, and you have this 50-50 splitter and these 2 detectors. Then these 2 independent Gaussian spots with the same point spread function, by simply multiply them would give you the square root of 2 gain in terms of resolution. Because you have no information, if you use it properly, you get the square root of 2 gain. So in real quantum experiment, you instead detect anti-bunching, basically that there is only 1 photon, or in a sense, you measure the absence of 2 photon correlations, but the amount of information is still the same. You still should be able to obtain this gain in resolution. And that's how actually it's practically done. You create this photoluminescence map, and then you do G2 at 0 delay map. So basically, in every single point, you get this G2 at 0 delay, and then you correlate the 2. And by doing so, you actually get the square root of 2 improvement. If you do the high order correlation measurement, let's say n order correlation measurement, then the increase would be square root of n. So, but of course, this is a very long characterization. Even for G2 measurement, it takes quite a long time, as I pointed out. And that's clear how machine learning could help this by simply doing these measurements much faster. And that's what is shown here. We actually collected this G2 mapping within a 5-second collection time. And this is the mapping of G2. And as a result, what we obtain, this is photoluminescence map, this is G2 map, this is the resolved image, which you obtain by correlating the 2, and you get this 12 times speed up. Instead of 17 hours, it takes only 1.4 hours. So to prove that indeed we have a better resolution, here you have this cross line through this photoluminescence spot, and here this resolved spot, and you do have increase by factor of square root of 2 as it's supposed to. So to sum up this part, so what we showed that machine learning clearly could speed up classification of photon emitters, whether it's single photon or not, by roughly a factor of 100. And moreover, in principle, it enables classification on the scale of 1 second, which is simply impossible with conventional approach. And also in terms of the super resolution, we also showed this 12-time faster super resolution imaging by through this anti-bunching effect and correlating the photoluminescence map and G2 map. Well, to take this idea, this point that machine learning could be very useful for designing this photonic circuitry, let me give you some more examples on what we're working right now. Basically clear, if you have a complex photonic circuitry, you could, by playing with shape geometry, You could optimize a single photon source in the spirit I just described. You could optimize cavities, couplers, guiding systems, waveguides, frequency converters. And the approach we're using to do this, it's based on this variational autoencoder for topology optimization, which is basically a system of coupled two convolutional neural networks, encoder and decoder. Encoder compresses features of training set into this compact latent space, whereas decoder learns how to read it and reconstruct. And the trick we're using here, we first do this optimization problem, which takes really long time and basically allows you to find this local minima. But as soon as you created this several optimization solutions, then you use it as a training set. And then you could produce very fast many different similar results, and eventually it could bring you to the absolute maximum. So the system works actually quite efficiently. Yet another interesting application of machine learning, in this case, we are trying to work with quantum machines or quasi-quantum machines. As already was pointed by Chris, so that there are hot, exponentially hot problems. And it's known that so-called QBER, or quadratic unconstrained binary optimization, actually this formalism can be applied to hot combinational optimization problems, such as traffic flow or this traveling salesman or number partitioning. So basically it's about, mathematically, it's about doing this optimization for this function. But if I compare this function with Eisen model, you clearly could map one to another. So what we already did, I should say that work is done in collaboration with Sabre, and Blake Wilson is the leading guy in this effort, he's our student. So you simply let your system evolve and go to the ground state. I mean, for this D-wave machine, when you have this coupled spins, you have all these local magnetic field, this coupling constant. You let it evolve to the ground state, then you measure all these constants and you map it there, and that's the solution of your QBER problem. So which you obtain with D-wave. So now we are trying to do similar things, well, just thinking how to do it similar thing with really quantum simulators, such as the one which Quera runs, or of course what Chris showed today. So that's actually how we do it. The challenge is you have a continuous problem, nanophotonics problem, and you need to convert it to this binary problem. And for this, we use this binary variational autoencoder, which encodes continuous problem, such as, I don't know, optimization of diffraction gradient or TPV emitters. We tried already several problems into binary. It compresses space and then samples it with quantum-assisted QBER sampler. So that's the idea. But I guess the point here that classical nanophotonic problems, continuous problems, could be run and should be run with quantum machines. So the next thing I'd like to discuss with you is the silicon nitride platform. So if you really would like to bring something to industry, of course it helps when you offer something which they are already working with. And this is the most compatible platform. Silicon nitride is just a version of this. And it's known it works remarkably well for nanophotonics applications. It has smaller losses, like 2 photon losses, a higher refractive index. So this is a really wonderful platform. But so far, most of these quantum photonics efforts, we relied on hybrid approach. Basically, you bring single photon emitters and you couple them to the silicon or silicon nitride-based structures like waveguides. Or you use this spontaneous parametric down conversion, which is not deterministic, but rather probabilistic process and requires lots of infrastructure. So what we recently obtained is inherent single photon emitters in silicon nitride. So, and that's, I think, could be quite important development. Of course, something should be done differently because other people never observed it. And what we did differently, we used this high density plasma CVD to obtain this somewhat enriched in terms of nitrogen silicon nitride. So the ratio of nitrogen is higher than in conventional silicon nitride. Yet another very important critical step is to use this rapid thermal annealing. And I will say later why we think it's so important. When we do that, what happens, and that work done, I should say, by Sam. He did this with the magic, and there is a whole group, Alex Senichev, Zach, and others, and Xiaowei working on this project. What we obtained is that fluorescence background is dramatically suppressed, and that enables you to see these single photon sources at room temperature. So we get routinely G2 below 0.2, in many cases just 0.1 or even less. Photoluminescence peaks occur at virtually the same wavelength, which mean that the reason for this single photon emission is actually one particular defect. We still don't know what is that defect, but I would speculate more what we know about this, actually, or guessing about this. And of course, this could be direct, scalable, and low-loss integration of quantum light sources with this well-established on-chip photonic platform. Here are just some examples. This is all very recent, I should say, studies. For example, here we look at 130 different emitters and put in this histogram G2 for different emitters. And for most of them, actually, it's below 0.2. So which is very good. It could be fitted with a 3-level system. And we get this low G2 or high quantum purity without any background correction or spectral filtering. So here, more information. They are stable. There is some blinking, but overall, they're quite stable. This is how a spectrum looks. It looks like it's overlapped 4 different spectral lines. But the important thing, it repeats from one defect to another one. It looks one in the same way. So we get at large enough pumping number of counts close to 1 million counts per second, billion photons per second, and it's linearly polarized. So what we did next, we integrated it with a waveguide, a silicon nitride waveguide, and they think here that we don't bring single photon source like, let's say, quantum dot or whatever. It's sitting right there. And we detect, we could couple it to waveguide mode with quite high efficiency, above 30%, which beats efficiency, which typically you obtain when you just couple it to quantum dots. But it could be further optimized up to 70–80% if you use some machine learning optimization. So, but it's already high. And then you use this decoupler, which outcouples with roughly 30% efficiency. Therefore, you get not instead of million counts per second, 20 counts per second, but it's still, sorry, 10,000 counts per second, but it's still very high. And G2 is pretty good. So we couple this single photon emittance to waveguides. And of course, the next step, make like thousands of them, put it on a chip and do some really cool stuff. So this is very interesting result obtained very recently, not published yet. So and that perhaps gives some idea what is the physical nature of these emitters. So what we made here is just pillars, silicon nitride pillars sitting on top of silica. So, and it looks like, this is hypothesis, not proven yet. So all this emission, all the single photon emitters occur exactly in the interface between silicon nitride and silica. And they occur because of the stress which you create when you do this rapid thermal annealing. Because expansion coefficients for silicon nitride and silica are different. And so when you do this thermal annealing, you create stress. And because of the stress, you get these single photon emitters at the interface. So ideally, it looks like 2D array because they're all sitting at the same XY position at the interface of single photon emitters. And the interesting thing, if you just choose 17 emitters in a line, not specially chosen, they all actually show anti-bunching, all of them anti-bunching. And about 50% actually go below 0.5. This is far from finally optimized. This is very first initial result. We certainly expect it further improved. So what is our hypothesis is that interesting thing happens. You need to create some critical value of stress to create this defect. And that depends in turn on the diameter of your pillar. So we work between 50 and 200 nanometers, and around 100 nanometers, you create this sufficient stress to have this single photon emitter. And then what we believe, something interesting happened. It's like, there is Coulomb blockade here, like stress blockade. As soon as you created one emitter, stress is released, and second emitter doesn't appear there. So if it's all true, then we would be able really to create this 2D array of nice quantum emitters. And so this still lots of work to do. We're going to now do these measurements at low temperatures, but it all looks very promising. So in that, I would like also advertise some activity we are doing within Quantum Science Center. This work done in collaboration with my colleagues from Anion, who spoke earlier today, as well as other folks. And in this effort, we try to bring together different quantum systems to create something more complicated, which could work as memory and as some kind of photonic system, spin. Specifically, in this particular case, we have spin qubit, for example, by using nitrogen vacuum nanodiamond, which couple to each other via magnets, because they are sitting on top of magnetic fields supporting these magnets. For example, coffee in this experiment. And you control this coupling through voltage, because this magnetic field is sitting on a ferroelectric substrate. When you apply voltage, you create stress converted to stress in magnetic field, and that moves the magnet bands, and therefore the coupling between spin through magnets also changes. We find it's quite promising in terms of making things like quantum memory, quantum repeaters, and reading them out optically. Like in this case, you read the spin state optically, and this readout actually could be plasma enhanced and speed up. This is a little bit busy slide, but illustrate the idea. So you have this nanodiamond sitting on this field that supports magnets. You apply voltage, it creates stress in ferroelectric substrate. This stress is transferred to this magnetic field. And because of this stress, you change the magnetization, both the direction and the amplitude of magnetization. And when that happens, the whole band for magnets, which is shown here, shifts. Let's say with no voltage, these magnets overlap with frequency of electron spin. And as a result, you have very strong coupling of magnets to spin, and therefore relaxation, spin relaxation goes very fast, which you detect optically. Then you apply voltage, you shift the whole magnet band. Now magnet band doesn't overlap with the frequency of electron resonance, and as a result, the coupling is much less, and the relaxation is much slower. And again, you read it optically. So you could control switch on and off this coupling between spins. You also could kind of reverse the problem. Here we use the electrical field to define the relaxation of magnets, so they're coupling to spin. What we do go the other way around. What if we measure these magnets and their spin relaxation, which depends on coupling to magnets, and find out what is the electrical field. And it turns out it could be a very good electric sensor. So, but in this case, we would like to have sharp magnet resonance rather than continuous bands, which are broadband and not that sensitive. If you simply pattern your field, you create these sharp magnet modes with relatively narrow resonance. And it turns out that sensitivity in detection of electrical field is expected to be by 2 to 3 orders of magnitude the sensor based on nitrogen vacancy. So it's magnet enhanced sense of electrical field. All right, it's time to wrap up. And I illustrated this idea that plasmonics, through this unique ability to confine electromagnetic modes way below the diffraction limit, like down to a few nanometers only, could speed up quantum processes to the extent that they outpace the decoherence. So that could enable interesting quantum devices. I illustrated this idea for single 4 nanometers, but it probably could be taken to other key elements of your quantum photonic circuitry, such as detectors, converters, and single photon nonlinearity. I also made the point that for really large quantum photonic circuitry, you really need machine learning, because otherwise it's hard to optimize your system, because you're dealing with very small signals with very sparse data. And that's exactly where machine learning could be very helpful. And I illustrated this idea, for example, by using some things like related to quantum measurements, metrology, quantum device optimization, and also the super resolution. So let me leave you with this outline, and which would remind you of what we discussed. And with this, I thank you for your attention.
Thank you, Professor Shalayev. Any questions from the audience? Immediate questions? Awesome. If not, you can keep submitting questions. We're gonna have a panel. So since we're actually early on time, we can have the speakers for today come up to the front and take a seat by their name. I'll pull up the slide and then we'll get started with our panel soon in a minute. Yeah. Yeah. here. So if we can have the panelists come by their name. All right, so you'll be able to just pass the mic around. All right, folks, if I can have you return to your seats, we'll get our panel started here. So we're gonna have this panel, it's gonna be pretty casual, but most of the theme are just mostly about quantum computing technologies, different materials platforms, and the speakers here can take it however they want over the next 45 minutes. We're gonna have this chat for about 25 to 30 minutes, and then we'll open it up to general questions. I received some questions before, and I'll try to loop them into our discussion as well. So again, here we have Professor Vladimir Shalaev, Professor Chris Monroe, and Professor Yang Chen. So starting with our first question, I think it's nice to admire what each other are doing. So I would like to ask each of you, other than the material platform for Qubit that you work on right now, what do you like the most about what the other panelists do in terms of the platform they have selected? So perhaps for Professor Monroe, obviously it's trapped ion, so maybe, and so on. So maybe Professor Shalaev and Professor Yang Chen would like to talk about what they like about each other's work, basically. So who, Professor Shalaev, would you like to start first?
Okay, maybe I'll start. Of course, it's highly speculative, but in my opinion, at least short term, we do need to have a quantum system which provide the highest possible control. And in that regard, in my partially biased opinion, array of ions is a really good way to go. That really provides lots of control of your system. Rydberg atoms also kind of in the same category. But in terms of long term, that's a more difficult question. So I actually like solid states. I think in the end of the day, devices which are compatible with kind of cheap type of industry, that certainly would eventually be more manageable. But that would require really different material platform, such as those Professor Chen was talking about. And that's really not only beautiful physics, which it is, it's fantastically beautiful physics when, as Chris pointed out, error correction actually is done by the system itself, which is topologically protected in these nanobillion anion excitations. Even though there is not single yet physical demonstration, at least convincing one, I believe that that's in the end might be a future for scalable quantum computing, which could deal with universal quantum problems, not like for example, photonics-based quantum computing is for me, no question about it's going to work, but as was pointed out, for each problem you have a different platform, which is kind of doesn't have memory. So it's not really probably good for universal quantum computing. So as I said, short-term system is very high control, like ions-based or let's say array of atoms is fantastic. And we probably will get lots of wonderful results with those systems and gain confidence, which is very important, confidence and trust of the public. But long-term, at least, I certainly hope that these beautiful systems, like potentially these quantum spin liquids, so basically those that support these nanobillion anion excitations, that could make a big difference as far as I see it. So I guess I covered all the platforms, but that's highly biased, my personal opinion. Feel free to disagree.
I'm forgetting the question. So how do we all fit into the, well, in this field, it's easy to do that, I suppose, because it's such a wide open field. I feel as though I studied for my first 20 years, I was really heads down into physics. It was atomic physics, which you could argue is probably more refined than other branches. On the other hand, the technology is, Bose condensation happened in a gas in 1995, and that's definitely physics, but it comes from atomic systems that we have all this control. And I think over the last 10 years, I've sort of jumped in a different, in a much different direction that's even higher than engineering or devices, is on application side of things. And I'm a little uncomfortable there because I'm not an expert in those things. Like even the idea of fault tolerant error correction, which is sort of a phase transition that happens when errors get low enough that they can sort of bootstrap, and you can do arbitrarily long computations if you have enough overhead. And that's beautiful physics in its own right. And we're starting to demonstrate aspects of that in our system. And so I love this field because it has so many different, everybody has a different direction, and we need it all. I do make the case that the system that I work with and know best, I will argue that it's the most mature right now. I think that may change in 10 or 15 years, but to get, and this relates to fault tolerant quantum computation. Some people, especially theorists, define fault tolerance as being able to do indefinitely long computations. Now to get there, which is possible, to get there will require incredibly low error rates, incredibly huge numbers of qubits. That's the trade space. If you burn 100,000 qubits for a single logical qubit, you can actually, using something called a surface code, which is a beautiful encoding technique that many in the solid state community are looking at right now. You could do arbitrarily long computations, and that's something absolutely worth going for. I think it's going to be fantastically expensive. We don't know how to get there right now, but to do small computations that are useful and valuable, that maybe have some error correction, but just a little bit, you're just leaking it in just to buy yourself a little more distance. The overheads won't be 100,000 to 1, maybe it'll be 10 to 1. And this is something that in my platform, that's when we think of error correction, we think of just leaking it in. Do as little error correction as you can. And I think the importance of that approach is that when it produces value, if I give you 100 qubits with 50,000 coherent ops before things fall apart, that's well beyond what you can simulate, what you cannot simulate classically. And I think to get there will require just going all out on the systems we have now. And it will pay for, I think it'll bring more interest into the field, commercial and otherwise. It will pay for full fault tolerance in the future. And so there's so many different directions. And I think, in your discussion of these wonderful topological systems that sort of have this natural, these emergent qualities of some condensed matter systems, they're very hard to understand, and it's not clear exactly where they will come from in real systems. We can actually simulate some of that stuff. It's a little bit contrived, but we can simulate it with a chain of 50 trapped ions. We can actually observe edge states that are, again, the Hamiltonian is a little contrived, but it can give you a little bit of a flavor for how to design a real system. That's really exciting. And so again, I have to sort of take lessons from condensed matter theorists, colleague friends of mine, and in our field to do that. But I think there's a friendly, fierce competition in the field, but it is very friendly because we're all counting on each other. I'm not a believer in zero-sum games. I think if some part of the field gets a lift, I think we all do. That won't be true in 20 years. Like if Intel goes up, AMD might not like it. When we get to that level of a commodity quantum computer, then things are different. But right now, it's just a wonderful time for the entire field. And I think there needs to be peer research. I won't claim I'm doing entirely peer research at the physics level, maybe at a higher level. But I think we all rely on each other. And so I think the three of us, totally different worlds in a way, but I think we all kind of rely on each other.
Yongchen, anything to add?
Thank you very much. Yeah, so it's really wonderful that even though I guess a lot from photon and atom for crit. You hear? It's already on? Okay, excellent. Yeah. So got photon, atom, I mean, maybe more electrons in my talk. But I totally agree with you. I think this dialogue is extremely helpful. Then in this, we have a new idea emerging, bridging AMO and condensed matter, very much driven by the development in many of the quantum information science ideas. So what I like about this question, back to your original question, that idea of the speed up quantum information process, I think it's always an idea very much like from Professor Shalab's talk. I think it's one of this powerful idea. I think it would drive a lot of further research in the sense if you, of course, to improve qubits and to reduce decoherence, that remains very important. It's very much a lot of research. But the alternative that in last talk, that to using, I guess you focus on the plasmonic approach, which is a very attractive approach to speed up quantum fingerprint process. So you kind of beat or get around the decoherence problem. May not work everywhere, but in certain applications, I think that's very promising. So if you act fast enough, everything can be quantum. I mean, if I allow you to, sure. I think I like that very much. I think it can be even go beyond the case perhaps you describe. I think that's very promising. Mm-hmm. Okay. Right, to try to go to the quantum region. Okay, that's one thing I liked. Now, in Professor Monroe's talk, I guess I heard you saying on the left side, you contrast several different platforms of qubits. You said AMO system, Purdue ions, has very well understood physics. That's kind of all engineering. I think that's so modest in a sense, because later, when you start to, maybe that's on the individual ion level, but when you have these now, even very small scale qubits, or you already have a powerful many body system, as you mentioned, you already can start to simulate or look at the entanglement entropy, perhaps something black hole. I also don't know much, but I know even a few many body system, already you're in the region, probably very, very difficult, fascinating physics in, many body entanglement. I think there's a lot of new physics, perhaps even unknown physics, it's already there. So that's very powerful. And that is an interface between AMO system and even more complex and even much dirtier, but fascinating condensed matter system. At that interface is very exciting how we can adapt some of the ideas developed in the small model, but already powerful system like the 10 qubit or 100 qubit ion quantum computer, how they measure entanglement entropy, to adapt some of these approach to solid state system. I think that's very, very interesting. So I like that part very much.
I guess in these responses, we're hearing a lot about, comparing to classical computers, like this concept of speed up. So I guess, and then Professor Monroe also discusses, it's almost like quantum computer, when will it work? If it works, it's almost like a black box. You can eventually, hopefully, you're platform agnostic. So as things stand, as you're surveying the field, as you're looking at literature and what have you, what are some, in terms of quantum computing or even just general quantum technologies, what are some key parameters that you look for, that you yourself set as a threshold as you're reviewing these papers? Is it fidelity? Is it like how they deal with decoherence times? Can you discuss briefly?
Okay, maybe I'll quickly start. So you brought up what I would call a component metric, like the fidelity of a 2-qubit gate, which is often the bottleneck in scaling. And very roughly, if you imagine your fidelity of a 2-qubit gate is 99%, you might expect to be able to do 100 of them before things really get to be, a very expensive noise generator. So you can only do 100 things. But these errors, we observe that they're not necessarily unbiased errors. They can have structure to them. And the more qubits you add, as you point out, more qubits you have, the more complex the errors can be. And error correction has been developed to take care of all possible unbiased errors, but that's probably in fact not going to be the right approach. I guess I lost my train of thought a little. What do I think about? If you want a simple metric, yeah, it's the 2-qubit gate fidelity usually, but that's not it. You really have to build a big system and see how these 2-qubit gates add up. Sometimes if it's a coherent error, if it's like a miscalibration, things were a tiny bit faster every time. Well, that's not necessarily bad. As long as you can calibrate it, you can mitigate for that without doing active error correction and so forth. So I don't know how to answer your question. What do I look for? I tend these days to look for very high level metrics, like do an algorithm. What was the success probability of that algorithm? It could be like the factoring algorithm. There are about a dozen other algorithms that are kind of useless. They're like toys, like Deutsch's algorithm, Bernstein-Vazirani, Grover's search algorithm, which is a little more useful. But the good thing about those algorithms is that they have a structure where they produce one answer. And the question is, what was the probability you got the correct answer? It's a yes or no question. You don't care about the 2 to the 25 other types of errors that can occur. You just need to know was it 50%? If you got a 50% probability of getting the right answer, that's pretty good. If it's 0.00001%, you're in trouble. So looking for different metrics, different algorithms have different complexities. They require different expression of gates, different connectivities. These are very high level architectural questions and low level component questions. And if you just do enough of them, they will test your system in a very clean way that will be independent of the hardware. What's the probability of the right answer? So I like that approach to verifying a quantum computer, because that's probably in 5 to 10 years when we actually are hopefully running useful algorithms, it will be one of those that it's actually doing something. So.
Well, I guess probably most would agree that error correction is a key thing, and to learn how to deal with all this, I think mature technologies. I fully agree that what Chris showed today is probably the most mature technology in terms of quantum simulation and computing. That's actually a very good test bed. And so because error correction takes more qubits than to run simulations, right? What is like n squared or whatever? Quite a number. But one more thing I'd like to add to this. So when we discussing like running different things in quantum machines, it requires different algorithms, like quantum algorithm, and Sabra is sitting here. He's one of those who developing this. I think that would be very important to open up the advantages of quantum machine fully to run and to start thinking actually in terms of quantum algorithms rather than classical ones, which we are used to.
I want to add one comment. I think maybe it's already a little bit alluded in your talk, Chris, is that what do you mean by solve a problem actually also differs depending on problem. For example, if you talk about factoring numbers, I mean, you can verify whether your answer is right by multiplying together, then whether you either get right or wrong. But in other problems like this traveling salesman, it will take tremendous time. You really, really want to find that the ground state or the optimal. But very often, I guess life is not perfect. We have to operate in the almost as good. And then if we wait for a perfect answer, it will take forever. But maybe it's if you can find a path that is within whatever a certain error bar, is almost as good as the solution. That's probably the practically already useful solution you go after. And that threshold would be much easier than to try to go to exact, really optimal solution. So I'm hoping there's more example of such that perhaps even an imperfect quantum computer, I mean, we're entering the NISQ era already, right? With the noise, with imperfection, perhaps full error correction difficult. I'm hoping there's a range of problem that a approximately good, useful enough solution can already emerge or be helped by the even relatively small or medium scale quantum computer and algorithm that takes into account we can deal with something useful, maybe not the true absolute solution, but something that already useful. I think that would be great.
So I guess I received this question earlier, and it kind of comes to tie in with the algorithm part to deal with error correction. So there's so much, and I think it's on theme for this week because we have so many engineer and physicists and just general scientists here. Like, as you're founding companies or as your research group expands, how much resources do you have to account for all these things in planning out projects, planning out tools in your systems, or can you still get away with being very focused on one area of a problem? Like, should every quantum research group that wants to be successful, do they need to dedicate people to algorithms per se, or do you think people, or is it more like you get more collaboration type situation? Are there resource sharing, or does every group kind of have to build out a whole set of infrastructure? Well, I guess for both.
Well, at a company level, company, certainly a small company is not going to do research. A small company exists, usually it's privately funded, and like it or not, whoever invests in the company, they want a return. It might be a low probability, but it's going to be a return. There needs to be a path to something that will give investors a return. That's not what research does, and that's not what research should do. Research, in a sense, goes its way, and it can be distracted. I mean, we've all been involved with research that was a failure, but some research that's a failure is not a failure. It tells you you're barking up the wrong tree. Time to do this. Oh, look at that effect. It totally obscured what I wanted, but I don't understand that effect. That's the beauty of research. You can sort of take it where it goes. Investors don't invest in research like that. I mean, exceptions are big companies that can direct a few % of their bottom line to fundamental research, realizing that some of it will create value. So a company has to have a path to commercial value. And in the case of IonQ, it's to have a commercial use case for quantum computers. And it better not be 25 years. I mean, if you're lucky enough to get investors that can wait 25 years, that's great. What is a good, so the question is, what is a good time horizon? Depends on the investor. And I will say, when IonQ was first funded by venture capitalists, they came to us actually, and they did have a long-term vision. It was of order 10 years, show a path to something in 10 years, which was odd. I think that's quite a long time frame, especially for a venture capitalist. That's not typical. So IonQ is a public company. They went public last October, and that transaction involved getting many investors together to launch the IPO. And it was, it wasn't 10+ years. It was more like, of order, 5 years, something like that. And there's a roadmap for the company it's in public domain. Public company has to be forthright about all that, and we are. So it's not without risk. but we feel that the technology is mature enough, we can identify the paths forward to hitting a level where we can create commercial value.
Immediate question from the audience. I lost my train of thought too. So I guess on the topic of getting distracted, what are some fundamental physics questions or fascination that if time wasn't an issue that you would focus on? Or maybe is there another alternative qubit platform that really intrigues you that might not be in your field, or maybe a couple of degrees of separation away that you would want to work on as an alternative?
That's a good question, actually. I mean, even though we have quite a number of different platforms now we are looking at with all their pros and cons, perhaps the most sophisticated one is based on topological quantum materials. But I still explore one particular idea coming from Kitaev, Alexei Kitaev, and I would not bet that there are no other approaches which actually could result in yet another material platform, which could be potentially even better than those we are considering right now. But one way or another, it certainly would be based on new fundamental physics. So like Kitaev's protagonistic paper, where he introduced these new states, it certainly was the beginning, and people started to think of new materials, new specific physics, which would enable this. But it starts with some great idea, but sometimes it goes the other way around. You look at complex system, and here you go, you see new opportunity. So we already have quite a number of platforms, but there is certainly no like one thing would solve all the problems. So they all have pros and cons, and we still keep looking. I don't know. It's a good question, and I think we should be open for other opportunities that might come. One thing is I see it's going to be like hybrid, depending on what kind of things you want to accomplish. You might want to play with different platforms. They should be complementary. Like I pretty much show that one way or another, photonics always will be part of any quantum system, because this is the best information carrier, which propagates at the ultimate speed. So it's like flying qubits if you want to use this. So photonics, I'm absolutely sure would be part of this. But other ingredients, that's a big thing, like memory, quantum repeaters, whatever you want to do. That's an open question, and we should be ready. That's what makes it exciting. New physics might come. So, and by training, I'm a physicist, actually theoretical physicist, but I'm now working in the engineering department. And the way I always say that the best engineering is based on truly fundamental science. And in many cases, breakthrough in fundamental science is related to kind of societal needs, some kind of need to development of new devices, like transistor was clearly in need. This first funny transistor, germanium-based transistor that Chris showed. So there was a need for that, clearly. And that actually helped to develop pretty much fundamental things. I agree, we're living in an exceptionally exciting time. If you just, like my kids are running here, they would see entirely different world, because it's all about information processing, and quantum computers open up something unparalleled, something what you cannot even compare with anything. So it's going to be entirely different world. But for us, let's say, for physicists or scientists, this is a great opportunity to look in wonderful, exciting physics. And that just reminds me this famous saying by a Russian academician when he was asked to define what is physics. He would say, physics is the way to satisfy your curiosity at the expense of taxpayers. And for us, with all this, should I say, obsession about quantum computers, we have a fantastic opportunity to look at new breakthrough type of physics. And who knows, maybe that physics would result in new platforms, which would be those that we are considering now.
So briefly, I'll double down on the photonics. I think I can't prove this, but I think when you build a really big quantum system, it's going to have to be modular. It's sort of like we build big CPUs. We build multi-core central processing units because the connections are too dense. You just can't put trillions of transistors on one chip and have them all wired. You have to build them with individual modules. And because it's a quantum system, these modules need to not talk to each other. To me, that sort of means they are photons. Because photons can go through free space, through fibers, with almost no loss. And so photonically active quantum systems, I think, are going to be there. I'm a physicist as well. We reserve the right to be surprised. Maybe, neutrinos, or, somebody figures out a way to get over that. And I'm guessing that this conversation probably never happened in the 1920s, but I'm imagining, say the 1920s or 1930s, people are at a panel talking about computers. They don't really have them yet. There's no Turing or Shannon yet. But somebody says, you know what? If anybody gets a memory or a computer, I bet it will involve electric currents to connect them all together. So I think photonics is going to be a part of any quantum platform going forward. And the last disclaimer is that yes, trapped ions are optically active.
Any alternative platforms you like to explore if you had the resources and time?
I maintain, I think we'll keep an open mind. I like electrons for one reason. Again, my discussion is not limited to quantum computing itself. I very much agree that new physics will emerge when you have this ability, this unprecedented ability. You can create very high quality, many individual quantum system, right? Could be single ions or could be other system together. We know many body system is a very fruitful platform that new fundamental fields emerge. One of the favorite example, we keep going back to this fraction quantum Hall system. I think is one of the really fascinating example. Despite it's just bunch of electrons in 2 dimensions interacting, Coulomb interaction is pretty much only thing, maybe in the magnetic field, that kinetic energy is quenched, so Coulomb energy. Yet, you could not, it's very hard to imagine you have so many hundreds of these, many body quantum states, right, fraction quantum states with topological order, with somebody who had non-ambiguous state, emerge in this seemingly very simple system, very clean 2-dimensional electrons in magnetic field. I mean, this has been studied for decades. So I think that's one of iconic example, many body physics, new physics emerge. Now we have seen ability to bring high quality, even small number, and the number is growing, other system together, creating these new many body systems. So I think I'm looking for lots of new surprises and new physics in the coming years. I think this, I absolutely agree. This is very fruitful area research. Probably something new comes, not just even impact quantum computing, maybe total new way of quantum sensing, but most exciting, some new technology we don't even have a name for, I think, right? So maybe even quote I think in my previous life, I studied mathematics, and there's very powerful set of problem called Hilbert's problem, maybe more than 100 years ago. I forgot which problem. Let's say it's from, but one of the big problem. Maybe the solution never came, but Hilbert says, but this is a hen that laid many golden eggs, something like so. The process to work on it have invented solved so many other important problems. I think the same thing is the quantum computing, the pursuit of this control quantum system, creating this very well engineered quantum, and this pursuit of quantum computing will generate so many other, both classical and quantum technology. And I think that's very exciting for both science and engineering.
Thank you. Before we open up the floor to the audience questions, I am just gonna follow through with some technical questions posed by some students here. First one is from Blake. I think this is addressed to Professor Monroe. So this is more technical, so quick pivot. How much of an influence does the polynomial that describes the ion trap well have on the gate fidelity? Do you require higher degree to achieve very high fidelities? What other practical engineering problems need to be solved to achieve high fidelities in ion traps?
Okay, yeah, that's a pretty detailed question. And I said earlier, about 2 minutes ago, that we need a modular approach I think that's probably true for any platform. So with trapped ions, I think we're probably, I should have said this, we're not going to put 10,000 ions in one trap. It'll probably be 50 or 100, maybe even less than that. But it's going to be some number. And the details of how they're confined is actually, it's not really, we don't think about it that much. I think I pointed that we shaped the potential to make the laser control a little easier, but we don't have to do that. So I think what we have in terms of our control of the potential, a quartic is just fine. It's enough. We don't need to control the 6th, 10th, 8th, 10th, and 12th order polynomials. That's really diminishing returns. But controlling the 4th one is useful. It makes the ions a little more equally spaced. So maybe I didn't answer the question that well, but the good news is that we're probably not going to have to deal with more than 50 or 100 ions in a single chain. We'll have many of those chains and we'll move atoms between them. I didn't have time to talk about that, and then eventually photonics to go through. But it becomes a very high-level architectural engineering issue. And I think the current technology dealing with static chains is sufficient, I would say.
And a second follow-up question before we open up the floor. It's about quantum sensors, and it's addressed to every one of you, but I guess maybe more particular to Professor Yongchen and Chilaev. For quantum sensing, in addition to the single qubit, people are employing qubit ensembles for better sensitivity. However, the random orientation as well as the interactions between them may also introduce unfavored spectrum broadenings and decoherence. Is there any technology that we can do to overcome such challenges?
Well, I just should say that to discuss specifically, we are working with Fermi National Lab, trying to improve their detectors for dark matter. And so we first tried to use simply classical machine learning to deal better with the information they collect. But the fidelity they have, it's already high. It's really hard to beat it. But what we learned that indeed, if you move from single independent qubits to a number of qubits, entangled qubits, that could help really to improve sensitivity. Of course, there are some problems to overcome when you go to entangled qubits. And as I like actually, as Chris, I believe, mentioned that bad qubit is a good sensor. Let's say you have n bad qubits. It's potentially good. It's particularly good sensor because it's exceptionally sensitive to any perturbation. And when you go from 1 qubit to n entangled qubits, sensitivity would be enormously high. But indeed, the problem how to keep this coherent superposition becomes harder and harder. And the way to overcome it, well, I mean, you could increase local coherence time. You could speed up the process again. Might be a kind of non-orthodox approach to this. Yes, it is harder, but there is clear benefit going from 1 qubit to n qubits in terms of sensitivity. And that's exactly what we are trying to do now with Fermi National Lab in a specific context to detect dark matter, like Lahag, Blake, actually working with those folks who collect data and trying to see what could be done here.
Of course, ensemble or even multiple sensor with issues like inhomogeneity or randomness could be issue, but it also may be opportunity. Well, first of all, in fields like NMR or even NV center, people have borrowed things like dynamic decoupling and technique to address some of those. Also, I think that I already mentioned the availability of things like classical computation technology, like machine learning, to help you to be able to manage a seemingly complex system with some help in the post-processing. That's a very powerful tool, I think should be applied more so that we don't have to be so afraid of randomness. If something, we can extract information, we can do more processing, and there's additional information that can be got out of that. And I'm all very excited about that picture I think I showed with N that you mentioned, N quantum, N qubits, even it's back qubits, that looking at a many-body quantum system. I think this opportunity is very new, that now in principle, you have opportunity to kind of interrogate, have N signal source, and have this endpoint correlation. That is really unprecedented before, at least in condensed matter system. And we don't know, I mean, in the case NV, I guess you know, it probes some kind of a magnetic fluctuation into the correlation. It's still a little bit challenging to get to the atomic scale kind of correlation. But this kind of idea really need to be developed further, both theoretically and experimentally. I think that's a great opportunity, even if they are different, even they have suffered from randomness.
I got to mention Omer. Omer actually suggested this idea to use N qubits. The question must be coming from you. You might have an answer. Any good question implies that you already know the answer.
Attribute that question to be a good host here. Question was from Wen Chi Tong, who goes to here. So someone who knows what they're talking about. We have about 3-4 minutes left. Do we have any questions from the audience?
My high level view of quantum simulation is that it is restricted quantum computing. It's a quantum computer where you may not have full control of the Hilbert space. You may not have the ability to do every possible entangled state. I guess that's a definition, but it does something more interesting than just some global, very simple thing. So you raise a great question. I think anybody that claims to have a quantum computer is almost certainly running quantum simulations right now in many different contexts. And it comes down to tunability. If your system can only simulate itself, and it's an oddball model, my own research is guilty of that. We have the long-range icing model where it has weirdo phase transitions that you don't expect to see in material because material is local. Nevertheless, it has interesting mathematical kind of features. And we have limited tunability. We have this long-range icing model that has a power law range, 1 over distance to some power, and we can tune that power between 0 and 3. And so there's very interesting dimensionality studies. It looks like a 1D chain, but if the power law falls off slower than 1 over d, 1 over distance, then it's actually not one-dimensional by some arguments, right? So they're interesting. You can't calculate ground states for some of these models, but it's restricted. You have this global tunability that doesn't allow you to poke at an individual spin, for instance, like a quantum computer would be able to do. So I think it remains to be seen. So maybe the follow-up to your question is, well, why aren't people paying for that? Well, it's research. It's not being used to, there's not enough tunability to find a new material that could be a super high temperature superconductor or something like that. Maybe that's in the future, but I would say it's still firmly in the research realm, these quantum simulators so far. I think molecular simulations, those are fairly general. They're called simulators, but they're really computations. You need really good control of the system. But there could be something, it's not black and white. I think there's everything in between. You do want more programmability in general to be able to extend your model to many different cases and maybe tune it to a real material that's out there.
I like the evolution of quantum simulator. It's increasingly become more, not just simulating known physics, but become a platform. You may call it synthetic quantum matter. I think a lot of it is becoming a platform, these synthetic quantum matter that discovered or realize new physics that difficult to realize otherwise. One example, maybe this, I like this Rydberg blockade simulating or realizing quantum spin liquid. I think that's a good example. And study of many-body localization is another example that would be difficult. I mean, a lot of new physics. I think it's so I think we will see more of those. Of course, if you have a well-controlled individual qubit and put together, that's you're already doing quantum simulation for sure. Even without that kind of a quantum computer, some intermediate useful quantum simulator is already useful in these discovering new type of many-body physics in this synthetic quantum matter domain. And who knows? I mean, I think some years ago, there's even DARPA program trying to calculate the high TC D wave whatever Hubbard models phase diagram that to help guide the development of high superconductivity. So that was even maybe 10 years ago. I think as these quantum becomes more developed, I think the value for like material design, we could see some more interesting development in near future, I think.
All right, thank you for the responses and a great question, Vahagan. So that's all the time we have for this panel. Can we give a hand, please, to all our speakers today? Thank you for giving their valuable time. So to close out the day, is Professor Meyer here? Yes. No? Perhaps Professor Meyer will come around. So in that case, that concludes the main talks for today and all the discussions today. We have snacks and extra lunch boxes available outside. So you are feel free to stay around and mingle. And thank you guys for attending our first day. Yeah, and go enjoy the sun. I'll see you guys tomorrow.
Thanks, Morris.
Oh, also, if you have any trash with you, please take it outside to the big trash bag out.